There's a moment, most people have had it, even if they've never quite named it, where you're lying still and you suddenly become aware that still isn't actually what you are. The bed holds you. The ceiling doesn't move. And yet something in the back of the mind insists, not loudly, just with a low steady pressure, that this room is going somewhere. That the building, the ground beneath it, the whole surface you're resting on is in motion and has been the entire time. That's not anxiety. That's physics. And it's more literally true than it has any right to be. Before anything else, just a moment to say thank you. This is a self-funded project. No studio, no production team, just one person researching and writing and narrating, and the people who support it on Patreon are the reason it keeps going. If you've ever considered supporting the work there, that support genuinely keeps this space alive. The channel is called The Sleepy Physicist, and whether you found it last night or months ago, it means something that you're here. Now, the room is moving at approximately 370 kilometers per second relative to the cosmic microwave background. That's the oldest light in the universe, a faint cold glow left over from roughly 380,000 years after the Big Bang, when the universe cooled enough for atoms to hold together and photons to finally travel freely. That light fills all of space uniformly in every direction, and when astronomers look at it carefully, one side of the sky is very slightly warmer than the other. Not dramatically, 1 part in 1,000 maybe, but enough. The warmth is a Doppler effect, the same reason a siren sounds different arriving versus leaving. The Earth is moving toward one patch of that ancient light fast enough to compress its wavelength and away from the opposite patch fast enough to stretch it. Warm one way, cool the other. Simple in principle, strange in implication. We are not at rest, we have never been at rest. Astronomers call it the peculiar velocity, which is a good name honestly, though they mean it technically rather than poetically. In cosmology, peculiar doesn't mean strange exactly, it means leftover. It means the velocity that remains after you subtract out the expansion of the universe, after you account for the Hubble flow. The smooth outward drift of all matter from all other matter that's been building since the beginning. Strip that away, and what's left is peculiar, the extra motion. The motion that can't be explained by the universe expanding. The motion that needs a different cause. And it's not small. The solar system moves around the galactic center at roughly 220 kilometers per second. That's fast. But the whole Milky Way, the disk, the halo, everything, is also moving through space on top of that, at something in the range of 600 kilometers per second, relative to that same microwave background. Different analyses give slightly different numbers. The one that shows up most often is 631 kilometers per second, every second. Not in any direction you could point to on a map with confidence, though there is a direction, a rough patch of sky in the southern constellation Hydra or near it. The measurement is solid. The explanation for why is, well, that's where things get complicated. Here's what's odd about velocity at this scale. You don't feel it. Not even a little. The wool blanket doesn't shift. The water in the glass doesn't slosh. Nothing in the room gives any evidence of 631 kilometers per second of directional motion through the oldest light in the universe. And this isn't because the motion is imperceptible in some unfortunate technical sense. It's because motion, without something to measure against, is genuinely not a thing you experience. There's no wind. There's no drag. There's no friction with space. Space isn't a medium you push through. It carries you, and you carry it. And the whole arrangement moves together without a single surface to feel it against. Which means the only way to know is to look outward, to compare your position and velocity against something far enough away to serve as a fixed reference. The microwave background does this. It's everywhere, it's ancient, it's, as close as anything gets in this universe, a still backdrop. Measure your Doppler shift against it and you learn your speed. Measure the direction of that shift and you learn roughly where you're heading. The sky has a warm side, that's the direction of travel. Now, here is where things begin to bend. If the Milky Way has a peculiar velocity, if it's moving in a specific direction that the Big Bang didn't cause, then something must be causing it. Gravity, almost certainly. A gravitational pull strong enough to accelerate an entire galaxy over billions of years. Or perhaps a push from a region of unusually low density behind us, where mass thins out and the gravitational floor drops away. Probably both, in some proportion. Either way, the cause has to be massive. Cosmically, stubbornly, almost ridiculously massive. And we can look for it. That's the thing. We can point telescopes in that direction and start cataloguing clusters of galaxies, superclusters, walls of matter, anything with enough gravity to be responsible. And when astronomers did this, when they started mapping the flow of galaxies, not just ours but thousands of others, all exhibiting their own peculiar velocities, most of them pointing roughly in the same direction, what they found was a structure. A concentration of mass enormous enough to have a name, a rough location, a gravitational influence spanning hundreds of millions of light years. They called it the Great Attractor, and calling it that, it turned out, was both accurate and insufficient. What stays with you if you let it, what I keep coming back to when I sit with this particular fact for long enough, is not the speed. It's the direction. That somewhere in the universe there is a place that the Milky Way has been falling toward for billions of years. Not arriving. Falling toward. The destination may be unreachable, may be receding faster than the fall can close the gap, but the falling is real. Has been real since long before the Earth formed, since long before the first stars lit up, since the very early universe began clumping and curving and pulling at itself across distances that make the word enormous feel almost quaint. The room is moving. You are moving. Every atom in the body has been in motion in this direction for longer than atoms in this form have existed. That's not unsettling exactly, it's just true in a way that most true things aren't. You feel it when the thought lands properly, not physically, somewhere else. The great concentrations of matter that are likely responsible for this, the structures whose gravity bends the trajectory of entire galaxy clusters over cosmological time, are what the next several hours will quietly turn toward. Not all at once, not with urgency. This is not that kind of story, but the pull is there. It's been there. And the further we look in that direction, the deeper the question gets. Not because the answer hides, but because each answer, once found, seems to sit inside a larger frame still waiting to be named. The first structure astronomers identified in the direction of the flow wasn't the largest. It wasn't even, as it turned out, the main cause. It was an enormous wall of galaxies sitting partially hidden behind our own, in a band of sky where the Milky Way's own dust and gas makes observation difficult. The region astronomers gave the quietly defeated name, the Zone of Avoidance, not in a billion years, not as a projection, not as a simulation running somewhere on a university server, not as a theoretical extrapolation from data gathered over decades. Right now, tonight. while the house is quiet and the street outside has gone still, and whatever you had on earlier, the light, the noise, the low-level hum of the day, has finally faded out. The Milky Way is moving, directionally, fast. Fast is a word that loses meaning quickly at cosmological scale. Or rather, it keeps its meaning, but the meaning stops connecting to anything the body understands. So try this instead: 631 kilometers per second. 1 kilometer is roughly the distance you might drive to get coffee, or to reach the nearest intersection worth naming. 631 of those every second in a direction that can be pointed to on a star map, toward a rough patch of sky in the southern hemisphere that holds some of the most gravitationally dominant structures in the local universe. In 1 second while you read this sentence, the Milky Way moved further than most people will travel in their entire lives. And the second after that. And the one after that. What's strange, not philosophically strange, just genuinely strange as a physical fact, is that this motion isn't new. It isn't something that started recently, or that's building towards some climax. The Milky Way has been moving in roughly this direction, at roughly this speed, for a very long time. Billions of years, accumulated incrementally under the gravitational influence of structures so large that they dwarf anything we've yet named. The velocity we measure tonight is the same velocity, more or less with small variations, that existed before the Earth formed. Before the solar system coalesced from a rotating disk of gas and dust around a young sun, before any of this. The motion predates us by an amount that the word predates doesn't really handle. I was reading about this, actually reading papers, the dense kind with tables of redshift corrections and footnotes about survey methodology, and I had a moment where I had to put it down, not because it was confusing, because it was clarifying in a way that felt almost uncomfortable. Sitting at a desk with a cooling cup of tea and a window showing an ordinary suburban street. And the ground under that street, under the foundations, under the bedrock, all of it moving at a speed that would cross the continental United States in roughly 5 seconds. The ordinariness of the desk didn't change, but it sat differently after that. The local group moves with us. That's worth pausing on. The local group is the gravitational family the Milky Way belongs to, a few dozen galaxies bound to each other, the largest of which are the Milky Way itself and the Andromeda Galaxy. 2 roughly similar spirals that are, separately, also falling toward each other on a collision course about 4.5 billion years away. But the whole group, Andromeda, the Milky Way, the Magellanic Clouds, the smaller satellite galaxies scattered around them like debris, all of it moves together. Not identically. Each member has its own additional local motion within the group. But the bulk velocity, the directional drift, is shared. The local group is moving at roughly 631 kilometers per second in the same direction, pulled by the same gravitational sources. It's not just us. It's the whole neighborhood. The reference frame for this measurement matters, and it's worth being specific about it. The speed isn't measured relative to a neighboring galaxy or a nearby cluster. It's measured against the cosmic microwave background, or the CMB, which functions, for these purposes, as the closest thing the universe has to a truly fixed backdrop. The CMB fills all of space. It has no preferred location. Every point in the universe is, in some sense, equidistant from its origin. When astronomers measure the Milky Way's velocity against it, they're measuring against something as close to absolute as anything in a relativistic universe permits. The result is a dipole. One side of the CMB sky fractionally warmer, the opposite side fractionally cooler. The temperature difference is tiny, thousandths of a Kelvin. But it's there. It's consistent, and it tells us not just that we're moving, but how fast and in what direction. CMB doesn't care what we think about it. It just records the Doppler shift and lets the arithmetic do the rest. Here is the thing that took me a while to really absorb, and I'm not sure I've finished absorbing it. The Milky Way's peculiar velocity, this 631 kilometers per second of directional drift, is not caused by the Big Bang. The Big Bang produced expansion, which is a different thing entirely. Space itself stretching, all matter moving away from all other matter, no preferred direction, no center. Peculiar velocity is what remains after you subtract that expansion out. It's the motion above and beyond the Hubble flow, which means it has a cause that is local, comparatively speaking, structures within the observable universe that are massive enough to bend the trajectory of everything around them over billions of years. And here is where the central metaphor of this particular question becomes useful. Or, not metaphor exactly, more like an analogy that actually holds up physically. Water on a tilted surface flows toward the low point. Not because the water wants anything, not because the low point is calling to it, just because the geometry of the surface creates a gradient, and objects on a gradient move. In cosmology, the equivalent surface is the large-scale distribution of matter. Where matter concentrates, it curves space-time. Where spacetime curves, other matter falls toward it. The tilt is gravitational, and the Milky Way, like every other galaxy in the local universe, is on a slope, has been on a slope, and the slope leads roughly toward a region of sky that contains some of the largest concentrations of matter within 1 billion light-years. The Milky Way is water on a tilted table. The tilt is real. The direction is measurable. What's at the bottom of the tilt is still being mapped. That mapping is genuinely hard. Not as a complaint, just as a fact about the geometry of the problem. The structures responsible for the flow are mostly in a direction that our own galaxy partially obscures. The galactic plane, the disk of the Milky Way loaded with gas and dust, lies between us and a significant portion of the relevant sky. Optical telescopes can't see through it. Radio and X-ray telescopes can partially penetrate it. But there's a band of sky roughly 20 degrees wide, where the view is severely compromised by our own position inside our own galaxy. Astronomers have a name for this region. It's called the Zone of Avoidance, and it sits, with almost deliberate inconvenience, directly across some of the most gravitationally significant territory in the local universe. So the picture being assembled here, slowly survey by survey, cluster by cluster, is of a Milky Way that is not drifting randomly. It's falling or being pushed, or both, in a direction that can be specified, at a speed that can be measured, toward causes that can be partially identified. Partially. That word is doing a lot of work in this subject. Every structure discovered in the direction of the flow has turned out to contribute to it, but none of them so far has fully accounted for it. There's always residual velocity left over, more pull than the identified sources can explain, which either means the surveys are incomplete, which they certainly are, or something else is contributing, something further, something larger, something that the instruments haven't fully resolved yet. Or, and this is the possibility that sits at the back of all of this, the one the data occasionally seems to reach toward, something that may not be inside the observable universe at all. The body has been travelling in this direction for every moment of its existence. The atoms that make up the hand resting on the blanket were once scattered through a molecular cloud that was also, at every moment, being pulled in this direction. The direction is not random. The gravity is real. And the source of that gravity is, out there, in the rough direction of Hydra, past the Zone of Avoidance, past the Great Attractor, past the Shapley Supercluster, still only partially resolved, still pulling, still accumulating redshift surveys and X-ray maps and competing theoretical explanations from astronomers who have spent careers pointing instruments at a region of sky that keeps yielding new reasons to keep looking. There's a structure in that direction that wasn't named until 2014. It had always existed. The galaxies were always there, the gravity was always real, but nobody had thought to trace the flow lines back far enough to see the full shape. When they did, the structure they outlined was larger than anything that had a name. 500 million light-years wide, and the Milky Way sits somewhere near its outer edge, falling inward along with 100,000 other galaxies, all of them following the same slow geometry. They called it Laniakea, immeasurable heaven. The problem is this: you cannot point at it, not directly, not with any telescope currently built or likely to be built. The thing doing the pulling doesn't announce itself with light. It doesn't sit at a visible coordinate waiting to be catalogued. What it does, the only thing it does from the perspective of anyone trying to find it, is make things move. Galaxies, clusters, superclusters. Everything in a wide region of space is drifting in a direction that the expansion of the universe alone doesn't explain, and the cause of that drift is somewhere in that direction, and the only way to find it is to watch the drift itself and work backward. This is detective work. Slow, cold, largely thankless detective work conducted across distances measured in hundreds of millions of light-years. There's a particular kind of frustration in cosmology that doesn't get talked about much, the frustration of indirect inference. Of knowing something is real, being mathematically certain it must exist, and still having no direct image of it, no spectrum, no clean data point you can hold up and say, there, this is it, this is the thing. Dark matter lives in this frustration. The Great Attractor spent decades there, and you build a case from residuals and anomalies and velocity vectors that don't behave the way they should. And at some point the case becomes overwhelming and the thing gets a name, and the name makes it feel more solid than the evidence technically warrants. Naming things does that. It shouldn't, but it does. Here is the basic method, stripped down. You survey galaxies, thousands of them, tens of thousands, spread across as much of the sky as you can access. For each one you measure two things: the redshift, which tells you how fast it's moving away from you due to cosmic expansion, and anything else you can use to infer its true distance. The brightness of certain standard candles, the relationship between a spiral galaxy's rotation speed and its luminosity, things like that. The difference between where a galaxy should be based on pure Hubble expansion and where it actually is, that difference is the peculiar velocity, the leftover motion. Do this for enough galaxies and a pattern emerges. Not randomly scattered deviations, a coherent flow. Thousands of galaxies all nudged in roughly the same direction, their velocities slightly higher toward one patch of sky, slightly lower toward the opposite. The pattern in the velocities is a map of the gravity. You're reading the floor by watching everything slide. The technique has a name: peculiar velocity surveys, and it's been refined over several decades through progressively larger catalogues and better distance indicators and increasingly sophisticated statistical methods for separating real signal from noise. The early surveys in the 1970s and 80s were crude by current standards. Small samples, large uncertainties, enough to see that something was there, but not enough to characterize it properly. The researchers who published the first systematic evidence of a large-scale flow toward what they called the Great Attractor, a group that became known informally as the Seven Samurai, which is the kind of name that sticks, were working with data that, by today's standards, would barely qualify as a preliminary sketch. They saw the shape in it anyway. That's the part that stays with me, not the technique, the nerve of it. I was looking at one of the velocity field plots from a more recent survey, the kind of diagram where each galaxy is represented by a small arrow showing the direction and magnitude of its peculiar motion. And the thing that struck me, sitting there with the image on a screen at some late hour with the lamp making a yellow circle on the desk, was how much it looked like weather, like a pressure map. Isobars and fronts and regions of convergence, arrows curving inward toward concentrations spreading outward from voids. The universe at this scale has weather, kind of. Not temperature-driven, not atmospheric, but the same basic logic. Gradients in density create flow, and the flow reveals the gradient, and the gradient is just another word for the shape of the mass distribution underneath. That analogy has limits. Almost all analogies at cosmological scale have limits, but it holds long enough to be useful. What makes the mapping genuinely hard, not just technically hard, but conceptually hard, is the zone of avoidance. The Milky Way's own disk, loaded with gas and dust, sits across roughly 20% of the sky and absorbs or scatters the light from whatever lies behind it. This is not a small problem. The structures most responsible for the local group's peculiar velocity are, with what feels like deliberate geometric spite partially hidden behind this obscured band, the Great Attractor, the Norma Cluster, Vela, a supercluster so large that its existence wasn't confirmed until 2017, hiding in plain sight behind the galactic plane for the entire history of modern astronomy. Radio telescopes help. X-ray telescopes help more in some respects. Neither fully solves it. There are reconstruction techniques, mathematical methods for interpolating across the gap using the velocity field data from the visible portions of sky. But interpolation is a word that always makes careful scientists uncomfortable. You are at some level filling in what you couldn't see with an educated guess shaped by what you could. The Laniakea paper VP, published in 2014 by Tully and colleagues, the paper that named and defined the supercluster the Milky Way belongs to, used a technique called the velocity field reconstruction. The idea is to take a sufficiently dense, peculiar velocity catalogue and use it to computationally reconstruct the underlying density field, the full three-dimensional map of where mass concentrates and where it thins out. From that density field, you can then draw what are called the basin boundaries, the equivalent of watersheds, lines that separate regions where material flows toward one gravitational center versus another. Laniakea was defined as a basin, not a thing exactly, a region of space within which all material flows toward a common gravitational focal point. The Milky Way is inside that basin. So is the Virgo cluster. So are roughly 100,000 other galaxies. What the 2014 paper did, technically, was draw the edges of the basin correctly for the first time. The basin itself had existed for billions of years before anyone drew it. There's an understated strangeness to this whole enterprise that I don't think gets acknowledged enough. The object being mapped, the source of the pull, is not an object in the conventional sense. It's a region, a gravitational tendency. The Great Attractor is not a single thing you could photograph if you could only get the dust out of the way. It's a broad area of above-average density spanning tens of millions of light-years, within which several massive clusters sit, the largest of which, the Norma cluster, is itself just one node in a much larger structure. Mapping it means deciding what counts as part of it and what doesn't, and that decision involves choices about scale and boundary that are, at some level, human choices imposed on a universe that doesn't particularly organize itself for our convenience. The map is real. The thing being mapped is fuzzier than the map implies. And even with all of this, The surveys, the reconstructions, the velocity field maps, the X-ray observations penetrating the zone of avoidance, the careful accounting for every known cluster and supercluster in the relevant direction. The flow isn't fully explained. Add up all the identified mass, calculate its gravitational contribution to the local group's peculiar velocity, and you still come up short. The residual isn't enormous, but it's there. Consistent across different analyses, stubborn, pointing outward, in the same direction further than the known structures, towards something the surveys haven't fully resolved. Maybe it's just a matter of completeness. Maybe another survey, wider and deeper, will find the missing mass in structures not yet catalogued. That's the conservative reading, and it's probably right. Probably, one of the candidates for the missing pull sits about 650 million light-years away. Further than the Great Attractor, further than most of what the early surveys covered. It's a supercluster dense enough, massive enough, that some analyses suggest it contributes more to the local group's peculiar velocity than the Great Attractor itself. Harlow Shapley identified the concentration of galaxies in that region decades before anyone understood what it meant for the flow. The supercluster carries his name now, and it still doesn't fully close the gap. Begin with the size, because the size is the only honest place to begin, and even then it doesn't really work. 520 million light-years across. That's the number most papers use. Some say closer to 500. The difference, 20 million light-years, is itself larger than the distance between the Milky Way and the Virgo cluster, which is the nearest major cluster of galaxies to our own, and an object that, for most of the 20th century, astronomers considered impressively, almost intimidatingly far away. The margin of error in the size of Laniakea contains multitudes. 520 million light-years. The observable universe is about 93 billion light-years in diameter, so Laniakea spans roughly 0.5% of it. That sounds small until you remember that 0.5% of the observable universe is still a genuinely monstrous amount of space, containing a genuinely monstrous amount of matter, and that the Milky Way, with its 200 to 400 billion stars, its dark matter halo, its satellites and streams and ancient stellar populations, sits somewhere near the outer edge of all of it. A suburb so distant from the supercluster's gravitational heart that calling it a member requires a somewhat generous definition of membership. The word Laniakea is Hawaiian. It means immeasurable heaven, or sometimes translated as open skies depending on the source, and the astronomers who chose it, Brent Tully and his collaborators, who published the defining paper in Nature in September 2014, chose it carefully in consultation with a Hawaiian language expert. The name carries weight, not just culturally, though it carries that too. It carries weight because the thing being named resists naming. It is not a galaxy. It is not a cluster of galaxies, or even a cluster of clusters in the ordinary sense. It is a basin, a gravitational watershed, a region of space defined not by what is there, but by which way things fall. That distinction matters more than it might seem. Before 2014, the Milky Way was understood to belong to the Virgo Supercluster, also called the local supercluster, a structure about 110 million light-years across, centered on the Virgo cluster, which sits roughly 65 million light-years away, and contains more than 1,000 galaxies packed into a volume of space that would look, on a cosmic map, like a dense smudge near the center of a much larger, looser cloud. The Milky Way floated somewhere in the outer regions of this cloud, a minor member of minor group on the outskirts of a moderately significant supercluster. It was a reasonable picture. It was based on real data. It was also, as the 2014 paper quietly demonstrated, too small. The Virgo supercluster doesn't have clean edges. it never did. What Tully's team showed was that the velocity field, the pattern of peculiar motions among tens of thousands of galaxies, didn't respect the old boundary. The flows extended further, they connected. They converged not on the Virgo cluster alone, but on a much larger attractor, and the basin that drained into that attractor was 5 times larger than the old supercluster map had suggested. Laniakea didn't replace the Virgo supercluster. It absorbed it. The Virgo supercluster became a lobe, one arm of a structure that had been there the entire time, waiting for someone to trace the drainage correctly. The method Tully and colleagues used, reconstructing the cosmic velocity field from a catalogue of peculiar velocities, then computing the basin boundaries from that field, is, at its core, the same logic a hydrologist uses to map a watershed. Pour water on a landscape and watch where it goes. The ridgelines are where it splits. The valleys are where it collects. In cosmology, the water is matter. The landscape is the gravitational potential shaped by the distribution of mass, and the collection point, the attractor, is wherever the density is highest, wherever the curvature of space-time pulls most insistently. The central attractor of Laniakea, the point toward which all material within the basin is, in principle, falling, is called the Great Attractor. It sits in the direction of the Centaurus and Norma constellations, roughly 150 to 250 million light-years away, depending on which component of the broader region you're measuring toward. It is not a single object. It is a region of above-average density containing several massive clusters, the most prominent of which is the Norma cluster, enormous, influential, and this is the part that the 2014 paper didn't fully resolve, and that subsequent work has only partially answered, probably not massive enough on its own to account for the full peculiar velocity of the local group. The basin is real. The attractor at the bottom of the basin is real. But the pull is larger than the attractor explains, which means either the basin is bigger than mapped, or something outside the basin is contributing, or both. Both, it turns out. Almost certainly both. 100,000 galaxies inside Laniakea. That number comes up in descriptions of the supercluster often enough that it starts to feel like a formality. A large round number deployed for rhetorical effect. It isn't. It's an estimate based on survey completeness and volume, and the actual number is probably higher. Surveys miss things, especially behind the Zone of Avoidance, especially at the distances where individual galaxies become hard to resolve against the background. 100,000 is a lower bound that everyone is comfortable quoting. The real population of the basin is larger, probably significantly larger, and each of those galaxies contains, on average, very roughly, 100 billion stars. The arithmetic stops meaning anything long before you finish it. What the 2014 paper gave the Milky Way, which it had never quite had before, was an address, not a precise one, not even a particularly flattering one, somewhere near the outer rim of a supercluster, in a small group, on the edge of a larger filament, falling slowly inward along with everything else in the basin. But an address, a context, a sense of which gravitational neighbourhood the galaxy belongs to, and what that neighbourhood is doing collectively over time. The Milky Way is falling toward the Great Attractor. So is Andromeda. So are the Magellanic Clouds and the dozens of smaller galaxies in the local group. So is the Virgo cluster, enormous as it is. All of it, the entire contents of a basin, 500 million light-years wide, moving, slowly, over billions of years, at speeds that look fast on a human timescale, and glacial on a cosmological one, toward the gravitational centre of a structure that has no edges sharp enough to photograph and no mass concentrated enough in one place to point at cleanly. And yet the fall is real. The direction is measurable. The velocity is 631 kilometers per second, and it has been for longer than the Earth has existed. Here is where the metaphor that's been building in the background finally arrives, and I want to be careful with it because it's easy to overextend. A river, draining toward the sea, does not know it is in a watershed. The water molecules don't understand that the slope they're following is part of a geometry that extends hundreds of miles in every direction, that every tributary is connected, that the ridge separating this watershed from the next is real, even though it looks, from any given point on the water, like just another hillside. The water follows local gravity. The watershed is what that looks like from above. Laniakea is a watershed. The Milky Way is water, following local gravity, falling toward a concentration of mass it will very likely never reach. Because the universe's expansion is carrying that concentration away faster than the fall can close the gap. Dark energy sees to that. The fall is real and the arrival is, in all probability, impossible. The Milky Way will fall toward the Great Attractor for the rest of its coherent existence as a galaxy, and barring something dramatic in the physics, it will never get there. There is something in that worth sitting with quietly. Not tragedy exactly, not futility, just the particular character of a fall that has no landing. The name given in 2014 reshaped, in a quiet technical way, how cosmologists thought about supercluster boundaries and how they should be defined. Before Laniakea, superclusters were typically drawn by finding concentrations of galaxies and putting a circle around them, a density-based definition, essentially. Tully's approach was dynamical, define the boundary by the flow. Where did matter converge toward this attractor versus some other attractor? That line is the edge. It's a more physically meaningful definition, and it produces different, generally larger structures than the density approach. It also produces structures that are harder to reify. A density concentration you can image. A watershed boundary is a mathematical surface computed from a velocity field reconstructed from a galaxy catalogue with known incompleteness and uncertain distances. The boundary of Laniakea is real in the sense that the physics it represents is real. It is not real in the sense of being a wall or a membrane or anything the spacecraft could detect while crossing it. It is a description of which way things fall, and descriptions are not the same as things, even when the descriptions are accurate. That's a distinction cosmology has to make often, doesn't always make it comfortably. The question that the boundary of Laniakea immediately raises, and that the 2014 paper was careful not to overclaim about, is what Laniakea itself is falling into. A watershed drains toward a sea, but the sea is also part of a landscape, and that landscape has its own gradients, its own concentrations, its own larger basins that the watershed feeds. If the Milky Way is inside Laniakea, and Laniakea is defined by falling towards the Great Attractor, then what does Laniakea fall toward? That question points further, and further, as it happens, is exactly where things become strange. The voids are not empty. That's the first thing to say, and it's the kind of correction that sounds pedantic until you sit with it long enough to understand what it's actually correcting. When cosmologists use the word void, they mean something specific. A region of space where the density of matter is significantly below the cosmic average. Below average. Not absent. Not zero. The largest voids in the observable universe still contain galaxies, just far fewer of them, spread across far more volume, thin enough that the region reads as underdense on a survey map and gets coloured dark on the visualization and looks, to a casual eye, like nothing. But nothing is doing a lot of work in that sentence. The voids are full of dark matter, presumably, distributed even more diffusely than the visible galaxies that trace it. They contain gas, ionized and nearly undetectable. They contain the faint filaments at the very bottom of the cosmic web's hierarchy, structures too thin and too sparse to show up cleanly in most surveys. The voids are quiet, they are not absent. The cosmic web, that's the structure, the large-scale architecture of the universe, that the voids are the negative space of. Matter in the universe at the largest scales is not distributed uniformly. It never was, not quite, even in the earliest moments after the Big Bang. Quantum fluctuations during inflation seeded tiny density variations, regions fractionally more dense than average, regions fractionally less, and gravity, patient and relentless, amplified those variations over hundreds of millions and then billions of years into the structure visible today. Dense regions attracted more matter, grew denser, eventually collapsed into halos and then galaxies and then clusters. Underdense regions lost matter to their surroundings, grew emptier, expanded faster than the cosmic average, became voids. The result is a foam, a web, filaments of matter connecting clusters at their nodes, sheets of moderate density bordering the voids, and the voids themselves, vast, rounded regions of relative emptiness, occupying most of the volume of the universe. Most of the volume. By some estimates, voids account for roughly 80% of the total volume of the observable universe. The stuff, the galaxies, the clusters, the filaments, is the minority. The universe is mostly its own absence. The largest known voids are staggering, in a way that the word staggering fails to convey, which is a problem this subject runs into constantly. The Boat's void, one of the first large voids identified and still one of the most discussed, spans roughly 330 million light-years. You could place the entire Laniakea supercluster inside it and have room left. It contains within that volume only a handful of known galaxies, dozens, where a region of average density would contain thousands. When astronomers first confirmed its size in the 1980s, one of the researchers joked, apparently seriously, Shapley, that if the Milky Way had been located inside the Boat's void, humans wouldn't have known other galaxies existed until the 1960s. The nearest galaxies would have been so far away that even mid-20th century telescopes might not have resolved them. That detail lodged in my head the first time I read it, and never really left. The accident of location. The idea that the entire history of observational cosmology could have been different, delayed by decades, because of where in the large-scale structure our galaxy happened to sit. Now, the void's push. This is the part that doesn't get enough attention in casual descriptions of large-scale structure. Voids are not passive. They are not just the absence of attractors. They actively contribute to the motion of matter around them, because underdense regions have less gravitational pull than their surroundings, which means matter at the boundary of a void experiences a net force directed away from the void's center. The void effectively repels, not through any exotic mechanism, just through the straightforward logic of being gravitationally weaker than everything around it. Matter falls away from the void toward the denser regions at its edges. The filaments and walls that border the voids are, in part, built from matter that the voids expelled. The voids carved the web as much as the dense regions assembled it. Both processes happen simultaneously, two sides of the same gravitational geometry. In 2017, a team of researchers proposed that a significant portion of the Milky Way's peculiar velocity, the 631 kilometers per second directed toward the Great Attractor region, could be explained not just by the pull of distant mass concentrations, but also by the push of an unusually large void in the opposite direction. They called it the Dipole Repeller, a region of below-average density, roughly 600 million light-years away, in the direction of the constellation Gemini, on the far side of the local group from the Shapley Supercluster. The idea was that the local group is caught between two influences, pulled toward the dense structures in one direction, pushed away from the void in the other. Both forces add up in the same direction. Both contribute to the same measured velocity. The paper attracted attention because it reframed the question slightly. The question had always been, what is pulling us? The Dipole Repeller paper asked instead, what if part of what looks like pulling is actually pushing? Not a pull from in front, but a slope, dense on one side, empty on the other, and the local group sliding down the gradient the way a ball slides down a ramp that's tilted at both ends simultaneously. Whether the Dipole Repeller fully accounts for its proposed share of the peculiar velocity is still being worked out. The void is real. The underdensity in that region of sky is confirmed by multiple surveys. The question is its exact contribution, how it interacts with the other known influences, how it fits into the larger picture of flows and attractors and the overall shape of the local universe's gravitational landscape. These things are genuinely unsettled, not dramatically unsettled, not in a way that suggests the basic picture is wrong, but unsettled in the way that all active science is unsettled. The edges are blurry, the numbers have error bars, and competing analyses give results that overlap but don't quite match. Is the Dipole Repeller a major driver of our motion or a secondary one? The honest answer is, it contributes, and the precise amount is still being refined. Here is the quiet thing about voids that took me a while to properly register. The universe expands everywhere, but it expands faster in the voids. Dark energy, the whatever it is that drives the accelerating expansion, acts on all of space, but in regions where matter density is low and gravity isn't fighting back as hard, the expansion wins more easily. The voids are growing, not just because matter is draining out of them into the surrounding filaments, but because the space inside them is expanding faster than the space in the denser regions around them. The voids are getting bigger. The walls and filaments between them are getting squeezed, relatively speaking, into thinner and thinner sheets as the voids on either side expand toward each other. Over the very long term, billions of years out, timescales that make the current age of the universe look brief, the voids will dominate, the web will thin, the clusters will eventually become isolated islands in an expanding sea of near-nothingness. Too far from each other for light to bridge the gap, each one alone in what will look from inside it like an empty universe. That future is not close, but it is, by the best current understanding, where this is going. The weight of empty space, then, is real. Not metaphorically, but physically. The voids push, they expand, they shape the filaments that border them, and the clusters that anchor those filaments and the peculiar velocities of every galaxy embedded in that structure. The Milky Way's motion is not just a story about what lies ahead in the direction of travel, it is equally a story about what lies behind, the underdensity, the void-driven push, the gravitational thinness of the region the local group is moving away from. Both ends of the slope are doing the work. The attractor gets the name, the repeller barely gets mentioned, the physics doesn't distinguish between them. The structures responsible for the pull in front and the push behind exist within a larger architecture, the cosmic web, that itself has a history, a formation sequence, a set of initial conditions set down in the first fraction of a second of the universe's existence. The web didn't assemble randomly. It grew from seeds, and some of those seeds, amplified over 13 billion years, produced concentrations of matter large enough to bend the trajectories of superclusters. The largest of those concentrations, in the direction the Milky Way is falling toward, has a name that carries the weight of the person who first began to understand that the universe of galaxies was far larger and far more structured than anyone before him had been willing to say. The name came before the understanding. That happens in science more than people realize. A label gets attached to an effect, a phenomenon, a region of sky that's behaving wrongly, and the name shapes the way everyone thinks about the thing before anyone has properly figured out what the thing actually is. Great Attractor. Alan Dressler coined it in 1987, and the name stuck immediately, the way certain names do, because it carried exactly the right weight. Not a description, a presence, something immense unnamed drawing everything toward it from behind the dust. Before the name, there was just the anomaly, which is always how it starts. Go back to the 1970s and early 1980s. Astronomers have been mapping galaxy positions and velocities for years, cataloguing the redshifts of thousands of objects, building up a picture of how matter was distributed across the local universe. And in those surveys, something kept appearing that shouldn't have been there. Galaxies weren't moving the way the expansion of the universe alone would predict. There was a surplus, a coherent directional motion, thousands of galaxies all nudged in roughly the same direction, their velocities slightly elevated toward a particular patch of sky. The motion was systematic, not noise, not measurement error, not an artifact of the technique. A real effect in the data, repeating across different surveys, different methodologies, different teams. Something was pulling. The question was what and where and how much. The Seven Samurai is what they became known as. 7 astronomers, Alan Dressler, Sandra Faber, David Burstein, Donald Lyndon Bell, Roger Davies, Roberto Turlevich, Gary Wegner, who collaborated across institutions over several years, assembling peculiar velocity measurements for more than 400 elliptical galaxies spread across a wide swath of sky. Elliptical galaxies were useful for this because of a relationship called the fundamental plane, a correlation between a galaxy's size, its surface brightness, and the velocity dispersion of its stars. Measure 2 of those properties and you can infer the third, which tells you the galaxy's intrinsic luminosity, which tells you its true distance independent of redshift. True distance in hand, you can subtract the expected Hubble recession and extract what's left. The peculiar velocity, the unexplained motion, what the 7 Samurai found when they mapped the peculiar velocities of their sample was a coherent bulk flow of roughly 600 kilometers per second, directed toward a region of sky in Centaurus and Norma. The flow wasn't confined to a few nearby galaxies. It extended across tens of millions of light years. The Milky Way was in it, the Virgo cluster was in it, the Hydra Centaurus supercluster was in it, and was itself moving, not just anchoring the flow, but participating in it, swept along toward whatever lay further out. The paper appeared in 1987. The name appeared shortly after, and the name did what names do. It made the thing feel real before it had been located. Locating it was hard for a reason that remains stubbornly inconvenient to this day. The Great Attractor sits in a direction that our own galaxy partially blocks. The Milky Way's disk, laden with gas, dust, and billions of foreground stars, runs directly across the relevant part of the sky, absorbing and scattering the light from whatever lies behind it. Optical telescopes see almost nothing in that direction. The Zone of Avoidance, the band of sky where extragalactic observation becomes difficult or impossible, lands with what feels like deliberate geometric spite right across the region astronomers most needed to examine. The core of the Great Attractor is about 7 degrees off the galactic plane. 7 degrees, just far enough to be frustrating, not far enough to be visible. Radio telescopes helped a little. Infrared surveys, which can penetrate the dust more effectively than optical wavelengths, helped more. The infrared astronomical satellite in the 1980s and early 1990s identified galaxies in the zone of avoidance that optical surveys had missed, refining the picture. And in the mid-1990s, X-ray observations finally revealed the cluster sitting at the gravitational heart of the region, a massive concentration of galaxies called Abell 3627, known more descriptively as the Norma cluster, located about 220 million light-years away, embedded in the zone of avoidance, detectable through the X-ray emission of its hot intra-cluster gas, even when the stars themselves were hidden. The Norma cluster, that's what's there more or less. When you finally look through the dust, a rich cluster of galaxies, among the most massive in the nearby universe, sitting at the center of what astronomers now call the Centaurus Wall, a large sheet of matter within which the Great Attractor region is embedded. It's enormous, it's gravitationally significant, and it's not enough. This is where the story gets a little awkward, and I want to be precise about the awkwardness rather than glossing over it. When the original mass estimates for the Great Attractor came in, based on the velocity field data from the early surveys, the numbers were large, very large, something like 5 times 10 to the 16th solar masses, which is a number so unwieldy it barely functions as a number. But as X-ray and infrared surveys gradually resolved the structures in the zone of avoidance and allowed more careful accounting of the actual mass present, the estimates came down significantly. The Norma cluster is massive. The broader Great Attractor region contains significant additional mass in the surrounding walls and filaments, but the total mass, the identified, catalogued, measurable mass in the region, doesn't fully account for the observed peculiar velocity of the local group. The arithmetic doesn't close. It's close, within the right order of magnitude, consistent with something real being there. But there's always been residual velocity left over after you account for everything in the Great Attractor region, which is either a matter of survey incompleteness, the dust still hiding something, or an indication that additional mass further out is contributing, or both, probably both. Some of the residual, it turned out, was coming from further away than anyone had initially thought to look, much further. I spent an afternoon once going through some of the early Bevan Samurai papers, not the summary articles, the actual papers, with their tables of galaxy velocities and their cautious, heavily qualified conclusions. The prose in those papers has a particular texture, the texture of people who knew they were onto something important but were genuinely uncertain how to characterize it, how far to extend the claim, how much the data could bear. There's a paragraph in one of them where Lyndon Bell and colleagues describe the bulk flow and then immediately start hedging, listing the assumptions the result depends on, the ways the measurement could be contaminated, the degree to which the model simplifies the actual geometry of the mass distribution. It reads like scientists being careful, which it is, but it also reads like scientists who were surprised by what they found and were doing their best to say it truthfully without overstating it. Here is what the velocities show. Here is what we think it means. Here is all the ways we might be wrong. That combination, confidence in the measurement, genuine uncertainty about the interpretation, is the actual texture of how this field has worked. The Great Attractor is real. The pull is real. What exactly is doing the pulling, and from exactly how far away, and in what proportions? That's been revised and refined and complicated repeatedly over the decades since 1987, and is still not completely settled. What the Great Attractor turned out to be in the framework that emerged from subsequent work is the gravitational heart of the Laniakea Supercluster, the central concentration toward which the entire contents of a basin 500 million light-years wide are falling. Laniakea was defined in 2014 not by the mass concentrated at the Great Attractor, but by the flow converging toward it. The Great Attractor is not a single object. It is a place, a region of elevated mass density, the Norma cluster at its core, surrounded by the broader Centaurus wall embedded in the larger architecture of Laniakea, that functions as the local minimum of the gravitational potential, the bottom of the bowl, the place the water runs toward. But the bowl is larger than the Great Attractor explains. The flow that the Seven Samurai measured in 1987 is real. The direction is correct. The amplitude Though the total peculiar velocity of the local group at 631 km per second cannot be fully accounted for by the Norma cluster and its surroundings. Something further contributes. Something at a distance that the original surveys didn't reach, that the early models didn't include, that became visible only when the catalogues grew large enough and the distance indicators precise enough to extend the analysis out past 500 million light-years. Harlow Shapley found it in 1930. He didn't know what he'd found. He called it a cloud. The metaphor that fits the Great Attractor, fits it better than I expected when I first reached for it, is a drain. Not a black hole. Nothing is falling in and disappearing. Nothing is being destroyed or consumed. Just a drain in the sense of a depression in a surface toward which everything in the vicinity slides. The surface is the large-scale gravitational landscape of the local universe. The depression is the Great Attractor region, and everything within several 100 million light-years, every galaxy, every cluster, every loose association of matter drifting through the void is on a surface that tilts, however gently, in that direction. The Milky Way is on that surface, has been on it for billions of years. The tilt is shallow enough that the journey would take longer than the current age of the universe to complete, and dark energy is ensuring the destination recedes faster than the approach. The drain is real. The falling is real. The arrival isn't. There's something in that particular combination of facts, motion confirmed, direction established, destination unreachable, that I keep coming back to when I sit with this subject long enough. Not metaphysically, just as a plain description of the situation. The Great Attractor is genuinely attracting, the Milky Way is genuinely falling toward it, and the distance will, in all likelihood, keep growing anyway. The anomaly that the Seven Samurai measured in 1987 has been confirmed, refined, extended, and partially explained by every major peculiar velocity survey since. The Norma cluster exists and is massive. The Centaurus wall is real. The Laniakea basin is real. But the peculiar velocity of the local group, when you trace it outward past the Great Attractor region, keeps pointing, past the identified clusters, past the wall, towards something behind it much further away that the early surveys couldn't see. The residual in the data was always pointing in the same direction as the Great Attractor, just further. As if the Great Attractor were the first answer to a question that turned out to be larger than the first answer could accommodate. The further answer, the concentration of mass that sits behind the Great Attractor at roughly 650 million light-years, significantly more massive, responsible for a substantial fraction of the local group's remaining unexplained velocity, carries the name of the man who first noticed the cloud in 1930 without knowing what it was or what it would eventually mean. The man who spent most of his career arguing that the Milky Way was the entire universe, who was wrong about that, dramatically, and who then spent the rest of his career mapping the thing he'd been wrong about with a kind of stubborn, systematic thoroughness that is, in retrospect, one of the more interesting second acts in the history of science. There is a band across the sky that astronomy mostly skips. Not officially. There's no policy, no agreed moratorium, no region formally declared off-limits by any institution. But in practice, in the accumulated habit of a century of survey work, a stripe of sky running along the plane of the Milky Way has been systematically undersampled, underrepresented, worked around rather than through. Optical catalogues thin out there. Redshift surveys develop gaps. Galaxy counts drop not because the galaxies aren't there, but because the view is obstructed, and obstructed badly, by the disk of our own galaxy sitting between us and everything behind it. The band is called the Zone of Avoidance. The name was given by Rubin and de Vaucouleurs in the 1950s, formalized by later usage, and it is stuck with the mild embarrassment of a label that says the quiet part out loud. We avoid it. Not because there's nothing there, because there's too much of our own galaxy in the way. What the obstruction consists of physically is gas and dust. The Milky Way is a disk, roughly 100,000 light-years across, and a few thousand light-years thick at the disk plane itself, and the disk is not empty. Between the stars there is interstellar medium, hydrogen gas in various states of ionization, molecular clouds, ionized plasma, and most consequentially for observation, dust. Fine grains of silicate and carbonaceous material, microscopic, suspended throughout the disk in densities that are individually negligible but collectively opaque over the distances involved. A photon of visible light trying to travel from a distant galaxy through the plane of the Milky Way has to run a gauntlet of this dust. Most of it doesn't make it. The light is absorbed, scattered, its wavelength shifted, its brightness diminished by factors that can reach hundreds or thousands depending on direction. In the densest parts of the galactic plane, optical extinction is effectively total. The result is a band about 20 degrees wide, give or take depending on wavelength and direction, within which extragalactic astronomy using optical telescopes is nearly impossible. 20 degrees out of 360, roughly 10% of the sky, in each direction above and below the plane. So perhaps 20% total. Gone behind dust. 20% sounds manageable, and in many contexts it is. The universe outside the band is still 80% of the sky, which is an enormous amount to work with. Most cosmological surveys simply acknowledge the gap and proceed. Large-scale structure maps carry a missing wedge where the zone falls. Statistical corrections are applied. Models are built that account for the incompleteness. The community has learned to work around the gap rather than through it, and the work done outside the zone has been sufficient to build a detailed, well-tested picture of the large-scale universe. Except that the gap falls with what continues to feel like unreasonable bad luck across some of the most gravitationally significant territory in the local universe. The Great Attractor sits in the Zone of Avoidance. Not entirely. The Norma cluster, its densest component, lies about 7 degrees off the galactic plane, which is at the edge of the worst obscuration rather than fully inside it, and X-ray and infrared observations have managed to penetrate far enough to characterize it reasonably well, but much of the surrounding structure is deeper in the zone. The broader Centaurus wall extends into the obscured band. A significant fraction of the mass that contributes to the overall gravitational pull in that direction is sitting behind dust that optical telescopes simply cannot see through. There are also structures that were identified comparatively late precisely because of their position behind the zone. The Norma cluster itself wasn't confirmed as the core of the Great Attractor until X-ray observations in the mid-1990s revealed it through the emission of its hot gas. Before that, the region was known to be gravitationally significant. The peculiar velocity surveys told astronomers something large was there, but the thing itself was hidden. And then there is Vela. In 2017, a team led by René Kraan-Korteweg published a paper confirming the existence of a massive supercluster located behind the Zone of Avoidance in the direction of the constellation Vela. The Vela Supercluster, they called it. Its centre lies at a distance of roughly 800 million light-years, and it spans perhaps 300 million light-years across. It had been invisible to optical surveys for the entire history of observational cosmology, not because it was small or faint or distant in any unusual sense, but because it sits behind the densest part of the galactic plane, and even near-infrared surveys had difficulty resolving it against the foreground clutter. When radio and spectroscopic observations finally penetrated the zone sufficiently to confirm the structure, what emerged was something significant. The Vela supercluster has a mass comparable to the Shapley Supercluster. It sits in a direction partially overlapping with the general direction of the CMB dipole, the direction of the local group's peculiar velocity. Whether it contributes meaningfully to that velocity is actively being studied. It might. Given the direction and the mass, it's hard to argue it doesn't contribute at all. The question is how much, and whether accounting for Vela helps close the remaining gap between the identified gravitational sources and the observed peculiar velocity. The supercluster had been sitting there unidentified for the entire time cosmologists were arguing about what was pulling the Milky Way. The dust had been hiding part of the answer. Near-infrared surveys transformed the situation meaningfully starting in the 1990s. The IRAS satellite, the infrared astronomical satellite launched in 1983, provided the first systematic infrared view of the sky that could partially penetrate the zone, identifying galaxies that optical surveys missed. Later surveys, particularly the 2-mass redshift survey and the HIPAS radio survey, pushed further into the obscured band. Radio wavelengths, 21 centimeter hydrogen emission especially, pass through the dust almost unimpeded. A galaxy containing neutral hydrogen will announce itself in the radio band even when its stars are invisible. The HIPAS survey, conducted with the Parkes radio telescope in Australia, catalogued galaxies behind the zone using exactly this method, finding structures that optical surveys couldn't reach. The picture emerging from these surveys is that the zone is not empty of significance. It contains galaxy clusters. It contains filaments connecting structures on either side of the plane. It contains, almost certainly, some of the missing mass that would help explain the residual peculiar velocity of the local group. What exactly is in there in full detail remains, still today, incompletely mapped. The dust hasn't thinned. The surveys have improved but not resolved every question. There are still gaps in the gaps. There is something specifically uncomfortable about the Zone of Avoidance that I haven't seen many people name directly. It is not just an inconvenience in the data, it is a structural feature of our position in the galaxy. We are inside the disk. The dust that blocks our view is our own galaxy's dust. We can't move outside it, can't reposition the telescope, can't choose a vantage point that doesn't have the Milky Way's plane sitting across some fraction of the sky. Every extragalactic survey ever conducted, every map of the large-scale structure of the universe, has this missing wedge in it. Not because of any failure of instrumentation or technique, because of where we are. The Zone of Avoidance is, in that sense, a permanent feature of terrestrial astronomy. It will narrow as techniques improve and better infrared sensitivity, more complete radio surveys, eventually perhaps space-based surveys at wavelengths that penetrate even more effectively. But it will never fully go away. Some part of the sky will always be difficult, always incomplete, always requiring interpolation and inference rather than direct measurement, which means some part of what is pulling the local group is sitting probably in a region we can only partially see. The structures that have been confirmed in and around the zone, Norma, the Centaurus Wall, Vela, are real, well characterized, gravitationally significant. And they are individually insufficient to close the full accounting of the local group's peculiar velocity. Something else is also contributing, something further or something still hidden, and this is where the question opens up in a direction most cosmologists treat carefully, something at a scale that no survey yet conducted has been large enough to fully resolve. Whether the remaining residual in the peculiar velocity is explained by better surveys of known structures, by confirmed structures like Shapley at greater distances, or by something still uncharted, that is genuinely an open question. Not dramatically open, not in a way that threatens the basic framework, but open enough that every new survey in the direction of the zone is, in a small and real way, an attempt to see something that has been hidden since humans first started looking at the sky. The 21-centimeter hydrogen line, which passes through the galactic dust without obstruction, has become one of the principal tools for mapping galaxies behind the zone. When a cloud of neutral hydrogen in a distant galaxy emits at 21 centimeters and the emission reaches a radio telescope on Earth, the dust between them is irrelevant. The photon doesn't notice it. A galaxy that is completely invisible at optical wavelengths, absorbed, scattered, rendered blank, can still be detected in the radio band. It contains enough neutral hydrogen, which most spiral galaxies do. This technique has found hundreds of previously uncatalogued galaxies inside the zone, some of them in clusters of real gravitational significance. The map of the zone is filling in, slowly, incompletely, but filling in. Each new survey narrows the gap a little, finds a few more galaxies, refines the density estimates in the obscured band. The missing wedge in the large-scale structure maps is getting thinner at the edges, not gone. Getting thinner. The zone of avoidance is not in the end a problem of technology. It is a problem of geometry, of being inside a flat, dusty disk and trying to see what lies in the plane of that disk from within it. The dust will always be there. The plane will always cut across some part of the sky. The surveys will always have a gap where the Milky Way sits between us and the universe. What changes is how well we can peer through the gap, using wavelengths the dust cannot stop, and how well we can reconstruct what's there from the flow patterns of everything visible on either side of it. The flow patterns tell us something is there. The radio surveys are starting to confirm what. But the full inventory of what sits behind our own galaxy's plane and how much of the Milky Way's peculiar velocity it accounts for is still, right now, tonight, an incomplete answer to a question the data has been asking since 1987. One of the structures confirmed behind the zone, confirmed only in the last decade using surveys that would have been technically impossible in the Seven Samurais era, sits in the direction of a particular constellation and carries a mass comparable to the most significant concentrations in the local universe. The man whose name it eventually bore spent most of his career mapping galaxies he couldn't fully see with instruments he had helped develop, in an observatory perched on a mountain in California, driven by an instinct for scale that kept pushing him to look further than the consensus thought worthwhile. His name was Shapley, and in 1930, in a photographic survey of the southern sky, he noticed something. He didn't go to university to study astronomy. he went to study journalism. The School of Journalism at the University of Missouri wasn't ready to open yet when Harlow Shapley arrived in 1907. Delayed, still being organised, not yet taking students. He needed something to enrol in. He looked at the course catalogue, went through it alphabetically, found archaeology first and rejected it on instinct, then found astronomy and enrolled in that instead. Not a calling, not a lifelong passion that had been building since childhood, an accident of alphabetical order and an unavailable first choice. This is the actual origin story of the astronomer, whose name now sits on one of the most massive gravitational structures in the local universe. A closed journalism school and a catalogue sorted from A. What followed was not accidental. The accidental part lasted about a semester. After that, Shapley was ferocious. He finished his undergraduate degree, earned a fellowship to Princeton, studied under Henry Norris Russell, one of the most rigorous astronomers of the era, completed a PhD on the orbital mechanics of eclipsing binary stars. By 1914, he was at Mount Wilson Observatory in California, working with the 60-inch reflector, the most powerful telescope then operating. He was 28 years old. He had been doing astronomy seriously for 7 years. What he found at Mount Wilson, working through a program of systematic observations of globular clusters, would reposition the Sun and the Earth in the cosmic order more dramatically than anything since Copernicus. The Sun was not at the centre of the Milky Way. It was not even close to the centre. It was out into the suburbs, about 30,000 light-years from the centre, roughly 2/3 of the way from core to edge, in no particularly special location. The galaxy were vast, far larger than anyone had believed, and the solar system was a minor resident of its outer disk. Shapley calculated this by mapping the three-dimensional distribution of globular clusters using the period luminosity relationship of Cepheid variable stars to determine distances. The method was sound, the conclusion was correct. The numbers were off by a factor that would later be attributed to unaccounted interstellar dust. He overestimated the Milky Way's size, but the essential geometry was right. The Sun was not the centre of anything. This is the thing about Shapley that I keep returning to, the thing that makes him interesting in a way that goes slightly past his scientific contributions. He had an instinct, a stubborn, recurring instinct, for reaching toward the larger frame. Every time the evidence allowed for a bigger picture, he reached for it. When other astronomers were still placing the solar system at the galactic centre, Shapley pushed it to the edge. When the galaxy was being conceived as a modest star system, Shapley argued it was enormous. When the first surveys of galaxies were beginning to reveal patterns of clustering, Shapley was among the first to argue that galaxies themselves clustered, that the clustering had structure, that the structure had scale. He was right about all of this in the general sense, often wrong in the details, and spectacularly, famously wrong about one specific large thing. The great debate took place on April 26, 1920, in the hall of the National Academy of Sciences in Washington. Shapley argued on one side, Heber Curtis on the other, the subject being the scale of the universe and the nature of the spiral nebulae. Those faint, fuzzy patches of light visible in long-exposure photographs, whose distance and constitution were then genuinely unknown. Curtis argued they were external galaxies, separate island universes of stars comparable in size to the Milky Way, located at enormous distances. Shapley argued they were gas clouds within or near the Milky Way, that the Milky Way was essentially the entire universe, that Curtis's interpretation required distances so vast as to be implausible. Shapley had correctly determined that the Sun was far from the galactic centre, and he used that correctly determined large Milky Way to argue, essentially, that a large Milky Way left no room for anything else. He was wrong. His error was compound or subissim or bisomnios. Partly a measurement problem, partly a logical one, and partly the kind of error that comes from taking a correct insight too far. The universe was not just a big Milky Way surrounded by gas clouds. It was, as Courtois correctly argued, and Hubble confirmed 4 years later, with his Cepheid observations of the Andromeda Galaxy, full of galaxies. When Hubble's letter arrived, the letter showing the light curve of a Cepheid variable in Andromeda, definitively placing Andromeda far beyond the Milky Way's boundary, Shapley reportedly told a colleague, "Here is the letter that destroyed my universe." He kept working anyway. That's the part that matters here. The version of Shapley who received that letter and folded, who retreated into defending a position the evidence had refuted, doesn't exist. What actually happened is that he redirected. Within a few years of Hubble's announcement, Shapley was mapping galaxies. Between 1925 and 1932, he catalogued something like 76,000 of them, using photographic plates from the Harvard College Observatory, where he had become director in 1921. He wasn't mapping them with the goal of finding large-scale structure, not exactly. The concept of galaxy superclusters was still forming. But he was looking at the distribution, noticing the patterns, identifying regions where galaxies concentrated. In 1930, doing a photographic survey of the southern sky with the Bruce telescope at Bloemfontein in South Africa, he found a concentration of galaxies in the constellation Centaurus that he described as the most striking he had encountered. A cloud, he called it. Dense, elongated, notably rich in galaxies compared to the surrounding field. He estimated its distance at roughly 14 times the distance to the Virgo cluster, which, given current estimates of the Virgo distance, would put it at something like 900 million light-years, a bit further than modern measurements, but impressively in the right range for observations made in 1930 with a 24-inch telescope on photographic plates. He called it a cloud and moved on. He didn't have the tools to characterize its mass, its gravitational influence, its relationship to the motion of nearby galaxies. Those tools didn't exist yet. The concepts didn't fully exist yet. He just noticed it was there. I have a book that Shapley wrote in 1943, a popular account of galaxies called simply Galaxies. Picked it up second-hand somewhere, pages slightly foxed, the binding cracked along the spine where someone read it heavily. The prose is confident, sometimes grandiose in the way 1940s popular science writing often was. But underneath the rhetorical flourish there is a genuine intellectual excitement that still comes through. He writes about galaxy clusters with the enthusiasm of someone who finds the sheer fact of their existence barely believable, who hasn't quite gotten used to the idea that matter organizes at scales this vast. There's a section where he describes the Centaurus cloud, what we now call the Shapley Supercluster, and the writing is more speculative than the rest of the book, more tentative. He knows it's there. He knows it's large. What he doesn't know, what he couldn't have known, is what it means for the motion of the galaxy he's sitting inside. The naming happened in 1989, when Somak Ray Chaudhary published a systematic survey of galaxies in the region using UK Schmidt telescope plates and formally identified the concentration as a supercluster, naming it after Shapley in recognition of the 1930 survey. By that point, the Seven Samurai had already published their bulk flow paper. The Great Attractor had a name. The question of what was pulling the local group was live and actively debated. And the Shapley concentration, now formally a supercluster, the most massive in the local universe, was sitting in the direction of the flow, far enough behind the Great Attractor that the early surveyors had underweighted its contribution, massive enough that it couldn't be ignored. The core of the Shapley Supercluster has a mass around 1.3 times 10 to the 16th solar masses in a volume with a radius of about 12 megaparsecs. 25 or more clusters is within the supercluster boundary, some of them merging, the gas between them heated to tens of millions of Kelvin and emitting in the X-ray. The overall system extends over roughly 260 megaparsecs and contains a redshift range that reflects genuine physical depth, not just line-of-sight spread. It is not a projection effect, not an overdensity that flattens out when you add the third dimension. It is genuinely physically enormous, genuinely self-gravitating in its core. The core is collapsing rather than expanding with the universe, which is unusual, which tells you something about the density. Research suggests that the Shapley Supercluster may account for somewhere between 25 and 50% of the local group's peculiar velocity, a range that reflects the genuine uncertainty in the measurements, not evasion. Some analyses put it higher. The precise contribution depends on how you model the mass distribution, what survey you use for the peculiar velocity catalogue, and how you handle the zone of avoidance between us and Shapley. The number is not pinned down. What is established is that Shapley is a major contributor, possibly the single largest contributor, and that without it the observed motion of the local group cannot be explained. There is an odd layering to this history that I don't think has a clean parallel elsewhere in science. Shapley mapped the galaxy he was wrong about, got the wrong answer, had his error corrected by someone using a method he helped develop, accepted the correction, and then spent the rest of his career mapping the distribution of the things he'd been wrong about, the external galaxies, well enough to notice in passing the concentration that would eventually bear his name and be identified as one of the primary causes of the Milky Way's peculiar motion through the universe. He was looking at the right thing for the wrong reasons, or maybe the reasons don't matter at this scale. The 1930 photographic plates recorded the most massive concentration of galaxies in the local universe. Shapley noted it in a survey report. The gravitational significance of what he photographed would not be understood for another 50 years. What Shapley represents in the context of this particular subject, the question of what is pulling the local universe, is the character of how big answers arrive in science. Not suddenly, not cleanly, not with a single decisive observation. He found the cloud in 1930. It was named a supercluster in 1989. Its gravitational contribution to the local group's peculiar velocity was quantified through the 1990s and 2000s. The 2017 Dipole Repeller paper placed the Shapley concentration as the dominant single attractor in the local flow, contributing roughly equally to the peculiar velocity as the newly identified void in the opposite direction. 90 years between the photographic plate and the dynamical model. Science moves at a pace that doesn't respect lifetimes. Shapley died in 1972. The supercluster that carries his name wasn't named yet. The significance of what he photographed in Bloemfontein in 1930 wouldn't be clear for another 2 decades after his death. He found something important and didn't know how important. That happens, and still the accounting isn't fully closed. The Shapley supercluster contributes a substantial fraction of the local group's peculiar velocity. The Great Attractor contributes another fraction. The Dipole Repeller, the void pushing from the opposite direction, contributes comparably to Shapley. Together, these identified influences account for most of what's observed. Most, not all. The residuals are smaller than they used to be, tighter, harder to dismiss as measurement noise, but they persist. And the persistence of residuals in peculiar velocity surveys, after accounting for every identified structure within 1 billion light-years, is what points the question outward. Past Shapley, past the zone of avoidance, past the boundary where current surveys run thin. towards scales and distances where the data becomes sparse and the inferences become careful and the conclusions become necessarily provisional. Whether there is something further, something at distances that strain the surveys, or something beyond the observable horizon entirely, is the question that lives at the edge of this subject. It's not a question the data can answer yet. It can only point. In 2017, a paper appeared in Nature Astronomy that reframed the question of what drives the local group's motion in a way that had been overlooked for decades. It wasn't about what was pulling in front, it was about what was pushing from behind. And the two effects, the Shapley Attractor ahead, the void behind, turned out to contribute roughly equally to a velocity that had been attributed, for 30 years, almost entirely to attraction. For roughly 30 years after the Seven Samurai published their bulk flow paper, the implicit assumption in cosmology was this: the Milky Way is being pulled, not pushed, pulled. The peculiar velocity of the local group, 631 km per second relative to the CMB, was understood as the result of gravitational attraction from overdense regions in the direction of travel. The Great Attractor, the Shapley Supercluster, clusters and walls of matter whose mass curved spacetime enough to accelerate an entire galaxy group over billions of years toward a particular patch of sky. The question cosmologists were asking from 1987 onward was essentially a search for the source of that pull, a census of mass in one direction, an attempt to identify enough concentrated matter to account for the observed velocity. It was a reasonable assumption. Gravity attracts, mass concentrations pull, the flow was toward a dense region. The logic was clean and it was probably mostly right. Mostly. What the assumption missed, what 30 years of surveys and models and competing analyses had consistently underweighted, was the other side of the equation. Underdense regions push, not through any exotic mechanism, not through any force that isn't already in the standard equations, just through the straightforward arithmetic of gravity operating on an uneven mass distribution. In a universe where matter is not spread uniformly, a galaxy sitting between a dense region and an empty one experiences a net gravitational force directed away from the empty region toward the dense one. The empty region isn't repelling in any active sense, it's just contributing less attraction than the surroundings. The result, from the perspective of the galaxy in between, is functionally a push, a slope, a direction of decreasing gravitational pull that matter slides away from just as reliably as it slides toward the denser side. This was not a new idea in 2017. The physics had been understood for decades. What was new was taking it seriously as a major contributor to the local group's peculiar velocity. Not just a secondary correction, not a small adjustment to the dominant attractor picture, but a first-order effect comparable in magnitude to the Shapley pull itself. The paper appeared in Nature Astronomy in January 2017. 4 authors, Yehuda Hoffman at the Hebrew University of Jerusalem, Daniel Pomarède at C. A. Paris-Saclay, R. Brent Tully at the University of Hawaii, who had also led the Laniakea work 3 years earlier, and Hélène Courtois at the University of Lyon. They used a dataset called Cosmic Flows 2, a catalogue of peculiar velocities for roughly 8,000 galaxies, and applied a reconstruction technique called the Wiener filter, a statistical method for converting an incomplete noisy survey of galaxy velocities into a smooth 3-dimensional map of the underlying density and velocity fields. The reconstruction identified 2 dominant structures controlling the local group's motion. One was familiar, the Shapley concentration sitting in the direction of the CMB dipole, pulling. The other was new, or rather newly identified as dominant, a large underdensity, a void, sitting in the roughly opposite direction, in the northern celestial hemisphere, at a distance of about 16,000 kilometers per second of recession velocity, somewhere around 220 to 250 megaparsecs away, give or take the uncertainty. The bulk flow of the local group was closely anti-aligned with this void, meaning the Milky Way's motion pointed almost directly away from it. The void was pushing, or rather, it was failing to pull, and everything in the vicinity was sliding away from it toward the denser regions on the other side. Hoffman and colleagues named it the Dipole Repeller. The name requires some unpacking. Dipole refers to the fact that the local group's motion, when mapped against the large-scale structure, resolves roughly into a two-pole system, one attractor pulling from one direction, one repeller pushing from the other, the two aligned almost exactly opposite each other, and the Milky Way's velocity vector threading between them. The geometry is cleaner than the real universe usually allows. Most cosmological situations are messier, more multipolar, more tangled in competing influences. The Dipole Repeller paper argued that at the scale relevant to the local group's peculiar velocity, the situation was unusually, perhaps surprisingly well described by just two dominant structures, one dense, one empty, roughly equal in their contribution to the observed 631 kilometers per second. Roughly equal, that part is the unexpected result. Not that a void contributes, but that it contributes as much as Shapley. Half the Milky Way's peculiar velocity in this analysis comes from being pushed away from an empty region rather than pulled toward a dense one. The attractor side of the story had been the whole story for 30 years. The 2017 paper said the whole story was symmetrical. Here is where I want to slow down, because there's something in this result that's easy to move past too quickly. The Dipole Repeller was not directly observed. It was inferred. The void associated with it, a region of below-average galaxy density in the northern sky, in the rough direction of the constellation Gemini, is real and has been detected in the galaxy surveys. But the specific dynamical role attributed to it, the precise quantification of its contribution to the local group's peculiar velocity, comes from the reconstruction, from the Wiener filter applied to the Cosmic Flows 2 catalogue, from a model of the velocity field built up from 8,000 peculiar velocity measurements with their associated uncertainties and selection effects. Reconstruction is, and this is the word that careful cosmologists use when they want to be honest, a model-dependent inference. You put in the data you have, you apply statistical assumptions about how the velocity field relates to the underlying density field, and you get out a three-dimensional map that represents the most likely configuration of matter given what you observed. The Dipole Repeller sits near the edge of the Cosmic Flows 2 data volume, which means the reconstruction there is less constrained, more dependent on the assumed prior, more sensitive to what data is missing than what data is included. The authors acknowledged all of this. They were careful. They said the structure was predicted by the reconstruction and expected to be confirmed by future deeper surveys, not that it was definitively established. The distinction matters. I was looking at the velocity field visualizations that the team released alongside the paper, intricate three-dimensional flow maps showing streamlines threading through the local universe, bending towards Shapley on one side and diverging away from the repeller on the other. The Milky Way sits in the middle tiny, its motion vector threading almost exactly between the two poles. The geometry is striking, almost too clean actually, and I remember thinking, looking at it on a screen late at night with the room quiet and a cooling cup of tea going slightly stale beside the keyboard, that real data rarely produces pictures this tidy, which isn't a reason to disbelieve it. Tidy pictures can be real. Nature occasionally cooperates with clean geometry. but it is a reason to hold the result with the specific grip that active science deserves. Real finding best current data, awaiting confirmation from deeper surveys. The central metaphor for this chapter has been building since the first paragraph, and it is this: a ball on a tilted table, not a complicated metaphor. A ball on a tilted table rolls in one direction, toward the lower end, that's obvious. What's less obvious, until you think about it carefully, is that the tilt can come from two sources simultaneously. The low end can be lower, because a weight is pressing down on it from underneath. Or the high end can be higher because the support is lifting it from below. Or, and this is the relevant case, both at once. The table can be tilted by a combination of depression on one side and elevation on the other, the two effects adding together to produce a slope steeper than either would alone. The local group is the ball. The Shapley Supercluster is the weight on the low end, pressing down, making that side lower. The Dipole Repeller is the support under the high end, lifting, making that side higher. The slope between them is the 631 kilometers per second of peculiar velocity. Both effects are real. Both contribute roughly equally. For 30 years, everyone was looking at the weight and mostly ignoring the support. What happens to the Dipole Repeller in the long run is the same thing that happens to all voids over cosmological time. They grow. Matter drains out of them into the surrounding filaments and walls. The space inside them expands faster than the cosmic average because dark energy operates more effectively where gravity isn't fighting back. The void associated with the Dipole Repeller is already large, hundreds of millions of light-years across in its estimated extent. Over billions of years it will become larger still, emptier, a wider and deeper basin of low density that the surrounding matter continues to drain away from. The push will get stronger in some sense, or rather, the slope will steepen on that side as the void deepens. Though this happens on timescales that render the word stronger almost meaningless, cosmological time making slow what already felt impossibly slow on human scales, the 2017 paper predicted that future surveys, deeper and more complete than cosmic flows 2, would directly confirm the void associated with the Dipole Repeller by finding the below-average galaxy counts in that region. Cosmic Flows 3 and Cosmic Flows 4, released in subsequent years, containing progressively more galaxies with progressively better distance measurements, have continued to refine the picture. The void is real. The dynamical role attributed to it has held up. The quantification of its contribution remains somewhat uncertain. The error bars haven't collapsed entirely, but the basic finding that the local group's peculiar velocity is driven comparably by a push from one side and a pull from the other has not been overturned. What has changed slightly is the picture of how clean the dipole geometry actually is. Cosmic Flows 4 reveals that the local flow is somewhat more complex than a simple two-pole model captures. There are additional structures contributing. The alignment isn't quite as precise as the 2017 visualization suggested. The real universe is messier than the tidy, streamlined maps implied. This is expected. Models simplify. The underlying physics is always more complicated than the first-pass picture. But the Dipole Repeller is there. The void is real. And the idea that half of what looks like being pulled towards something is actually being pushed away from something else. That reframing is now part of how cosmologists think about large-scale flows. What this means for the broader question, what is pulling our universe, or what is tilting the table the local group sits on, is that the question itself was slightly wrong. Not wrong in a way that invalidates everything that came before. Wrong in the way that most scientific questions are eventually refined. The answer is right, but the framing needed adjusting. The pull is real. the Shapley concentration is really there, really that massive, really contributing significantly to the local group's peculiar velocity. But the pull alone doesn't tell the whole story of the motion. The full story requires the push too, requires knowing what's absent in the opposite direction as much as what's present in the direction of travel, requires looking at the empty regions with the same seriousness as the dense ones. That shift from looking only at what's there to also asking what isn't turns out to have consequences that extend well beyond the dipole repeller. Because the same logic applies at larger scales, and at larger scales the voids are bigger, the structures are less well mapped, and the question of what is and isn't there becomes significantly harder to answer. The dipole repeller identified the dominant influences on the local group's motion within roughly 250 megaparsecs, but the peculiar velocity surveys extend further than that, and at distances beyond 250 megaparsecs, at scales where the cosmic flow's catalogues become thin and the reconstruction becomes less constrained, the flow still hasn't fully converged. The bulk motion of galaxy clusters persists out to distances that identified structures can't fully explain. Whether that residual flow points to something simply unmapped, another attractor, another void, a structure the surveys haven't reached, or to something fundamentally more distant and strange, is where the subject quietly opens into territory that even the best current data can only gesture toward. The peculiar velocity surveys kept finding the same thing across different datasets, different methodologies, different research groups working independently, with different telescopes and different distance indicators on different continents over a span of nearly 4 decades. The finding was this: the coherent motion extends further than the models predict. Not by a little, not within the margin of error, not something that could be absorbed by a slight recalibration of the Hubble constant or a revised estimate of the Shapley Supercluster's mass. The bulk flow, the large-scale coherent directional motion of galaxies that cannot be explained by local gravitational sources, persists outward past the identified structures, past the distances where the Shapley pull should have done its accounting and closed the books, into regions of the survey catalogues where the data thins and the error bars widen and the conclusions get careful and hedged, in the way that conclusions get when the ground beneath them is genuinely soft. The surveys agree on the direction. They agree mostly on the rough magnitude. What they don't agree on, what has been argued about in papers and conferences and follow-up analyses since at least the early 2000s, is how far the coherent motion extends, and what, if anything, beyond the already identified structures, is responsible for it. To understand why this is strange, it helps to know what the standard cosmological model predicts about bulk flows. In a universe where matter is distributed according to the lambda c/dm model, the cold dark matter framework with a cosmological constant, the current best description of how the universe is structured and how it evolved, large-scale bulk flows should exist but should be finite and should converge. As you average the motions of galaxies over progressively larger volumes of space, the peculiar velocities should average out. The bulk flow should diminish, and at some scale, several hundred megaparsecs, the motion should become consistent with the overall expansion and the residual flow should be negligible. The universe, at large enough scales, is supposed to be homogeneous and isotropic, everything flowing in every direction in equal measure, no net drift. The surveys keep finding net drift at scales where the model says the drift should have averaged away. The flow keeps going, not dramatically. This isn't a crisis for the standard model, not a result that has sent cosmologists back to the drawing board entirely, but persistently, stubbornly, at distances of 200, 300, even 400 megaparsecs, Some surveys find coherent bulk motion at amplitudes larger than lambda CDM predicts at those scales. The problem is partly technical, and that needs to be said clearly before anything else. Peculiar velocity measurements are hard. The distance indicators, Tully Fisher, fundamental plane type 1, A supernovae, all carry uncertainties of 15 to 20% per galaxy, and those uncertainties propagate through the analysis in ways that can mimic or mask large-scale flows depending on how they're handled. Selection effects distort the apparent velocity field. The zone of avoidance creates gaps that require interpolation. Different surveys use different samples, different calibrations, different statistical techniques for extracting the bulk flow signal from the noise, and they produce results that are consistent in direction, but sometimes inconsistent in amplitude. So when different teams report bulk flows larger than the model predicts at scales of several hundred megaparsecs, the first and most defensible interpretation is, the measurements are difficult and the discrepancies are within the systematic uncertainties. That interpretation might be right, probably is, in part. But the discrepancies keep appearing. In survey after survey, refined by progressively better data, the bulk flow at large scales is either consistent with lambda CDM at the high end of its predictions or slightly above them. It never comes in low. The flow is always at least as large as expected and often larger. And that consistent directionality in the residuals, always too much flow rather than too little, always in the same general direction, is the kind of pattern that makes careful scientists uncomfortable in the productive way, the kind of discomfort that motivates the next survey, the next refinement, the next attempt to either confirm the excess or explain it away. There is a concept in fluid dynamics. I was reading about it one afternoon sitting in a patch of late sunlight, coming through a window at a low angle, the kind of light that makes dust visible in the air and makes everything feel slightly more still than it actually is. The concept of a coherence length. The distance over which a flow remains organized, directional, correlated with itself. In a turbulent system, the coherence length is short. Adjacent regions of fluid move in different directions, the flow is chaotic. There is no large-scale organization. In a laminar system, the coherence length can extend across the entire flow. The water in a slow river, moving in the same direction from bank to bank, has a coherence length as wide as the river itself. The bulk flows observed in peculiar velocity surveys have a coherence length that is, by some analyses, uncomfortably large. Larger than the standard cosmological model would produce, through the gravitational influence of structures within the observable universe acting alone. The flow is too organized over too large a scale. Too much of the local universe is moving in the same direction, too coherently for the identified sources to fully account for. Whether this means the sources are simply under-identified, more mass in known structures than current surveys have mapped, more structures beyond the survey boundaries that haven't been catalogued, or whether it means something genuinely strange about the mass distribution at very large scales is exactly the question the data is sitting on without answering. The Cosmic Flows program led by Brent Tully at the University of Hawaii and Hélène Courtois in Lyon has produced the largest and most carefully assembled peculiar velocity catalogues available. Cosmic Flows 1 contained a few thousand galaxies. Cosmic Flows 2, used in the Laniakea and Dipole Repeller analyses, contained about 8,000. Cosmic Flows 3 pushed to nearly 18,000. Cosmic Flows 4, released in 2022 and updated in 2023, contains over 55,000 galaxies with distance measurements compiled from 6 different techniques: Tully Fisher, fundamental plane, Cepheid variables, type 1, a supernovae, surface brightness fluctuations, and the tip of the red giant branch method. Each successive catalogue has better spatial coverage, better calibration, smaller systematic errors, and with each successive catalogue, the bulk flow at large scales has remained, not grown dramatically, not shrunk within the model predictions, remained sitting at the upper end of what lambda CDM allows, or slightly above it, at distances of 150 megaparsecs and beyond, pointing roughly in the direction of the CMB dipole, consistent with a coherent motion that the identified attractors and repellers within the survey volume don't fully explain. The flow goes further than the sources that have been found. That is the plain statement of the situation. The residual matters more or less depending on how you read the error bars. And honest people disagree about how to read the error bars. Some analyses suggest the excess bulk flow is statistically significant, above what lambda CDM predicts at the 2 sigma level or higher, which in cosmology is enough to warrant serious attention. Other analyses, applying different corrections for systematic effects, find the excess within the expected range. The disagreement is genuine, not manufactured. It reflects the real difficulty of extracting a clean signal from data that is inherently messy at the scales involved. What both sides agree on is that the question isn't settled. The flow is real. The direction is established. Whether the amplitude at large scales is anomalously high, and if so, what would explain it, is an open question that better data will eventually answer. Eventually. The timescale for that depends on surveys that are planned, but not yet complete, on catalogues that will contain hundreds of thousands of galaxies rather than tens of thousands, on the kind of patient accumulation of distance measurements that takes decades. The theoretical options for explaining a bulk flow that persists beyond what local structures can account for range from mundane to genuinely unsettling. The mundane option, the surveys are incomplete. There are structures, clusters, superclusters, walls of galaxies, at distances of 500 to 800 megaparsecs that the current catalogues haven't fully mapped, and whose gravitational influence on the local velocity field is real but underestimated. The Vela Supercluster, confirmed only in 2017 and still being characterized, is one candidate. There may be others behind the Zone of Avoidance, or in regions of sky where the peculiar velocity surveys are thinner. Fill in the missing mass and the flow converges. That's the conservative reading, and it's probably partially right. The less mundane option, the coherent flow at very large scales, is real and reflects a genuine feature of the large-scale mass distribution that the standard cosmological model doesn't fully predict. Some large-scale structure studies have found features, walls, filaments, voids, at scales approaching or exceeding the homogeneity scale, the distance at which the universe is supposed to become uniform. If the universe achieves homogeneity later or at larger scales than the model predicts, bulk flows could persist further than expected simply because the gravitational landscape remains uneven further out than assumed. And then there is the option that requires stepping carefully, that lives at the edge of what current data can meaningfully constrain, that involves not just unmapped structures within the observable universe, but the possibility that the bulk flow is being influenced by something outside it. That possibility, structures beyond the particle horizon exerting gravitational influence on the observable universe, sounds like it should be ruled out by basic physics. The particle horizon is the boundary of causal contact, the surface beyond which no signal has had time to reach us in the age of the universe. Things beyond it cannot have communicated with us, cannot have sent us photons or particles or any information. But gravity is not a signal in the usual sense. Gravity is a consequence of the curvature of space-time, and the space-time curvature outside our horizon is not causally disconnected from the space-time curvature inside it in a simple, clean way. The distribution of mass before and during inflation shaped the curvature of the entire universe, including the region that would become our observable volume. A sufficiently large mass concentration in the pre-inflationary or early post-inflationary universe could, in principle, have imprinted a gravitational influence on our observable volume that persists as a coherent flow even today. Whether this actually happens, whether the bulk flows observed in peculiar velocity surveys are a signal of such influence, is not established, is not close to established, is the kind of speculation that moves carefully between theoretical possibility and observational constraint. That requires extraordinary evidence to take seriously as more than a hypothesis. But the flow is there. It points somewhere. And the somewhere it points, when the identified sources within the survey volume are accounted for, is past the edge of the current maps and into territory that either contains structures not yet found, or raises questions about the reach of gravitational influence that the standard picture doesn't naturally accommodate. The river analogy, which has been threading through this subject since the first chapter's mention of bulk flow and cosmic drainage, runs into its limit here. A river has a source. You can walk upstream and eventually arrive somewhere. A spring, a glacier, a watershed in the mountains, that is definitively the beginning. The flow starts there and moves from there to the sea with a clear directionality and a definable origin. The bulk flow of the local universe has a direction. It has a measured amplitude. What it doesn't have, yet, is a confirmed source that fully accounts for it. The identified sources, Shapley, the Dipole Repeller, the Great Attractor, Vela, explain most of the motion. The residual keeps pointing further. And further in this context means past the edge of the surveys, past the structures that have been mapped, toward a region of the sky and a distance range where the data runs out and the inferences run thin, and the honest answer is that we don't fully know what's there yet. The river goes upstream, but the spring hasn't been found. Maybe the next survey will find it. Maybe it's hidden behind the zone of avoidance. Maybe the source is not a source in the conventional sense at all, and not a discrete concentration of mass that can be catalogued and characterized and plugged into the velocity field model, but a feature of the large-scale geometry that requires a different kind of description. That question stays open. The water keeps moving. There is a specific measurement that sits at the edge of this problem. A measurement made not with galaxy surveys or peculiar velocity catalogues, but with the cosmic microwave background itself, using a technique that looks not at the positions of galaxies but at the subtle temperature distortions that moving galaxy clusters imprint on the oldest light in the universe. The measurement was made in 2008 by a team at NASA's Goddard Space Flight Center. Its lead author called the result a dark flow, and the result, if it holds, points not just past the edge of current surveys, but past the edge of the observable universe itself. Put everything down for a moment. Not as instruction, more as an acknowledgement that there is a point in this subject where the accumulated scale of what's been described starts to press on the mind in a particular way, and it helps to just sit with that pressure rather than push through it. The Milky Way falling toward Shapley at 631 kilometers per second. The Shapley Supercluster sitting 650 million light-years away, itself probably part of a larger basin. The bulk flow extending past the survey boundaries, pointing toward something not yet fully identified. All of this has been building layer by layer, and it has been building toward a question that is different in kind from the questions that preceded it. The previous questions were about what is out there. This one is about whether out there has a limit, and whether a limit, if it exists, is actually a limit on what can pull. There is a room somewhere, a specific room in a specific city, with a specific quality of light coming through a window at a particular hour, where you might be reading this. The ceiling above that room is real, the floor is real, the walls are a specific distance from each other, and the air between them has a temperature and a smell and the particular texture wherever you happen to be tonight. All of that is right there, immediate, the most local thing there is, and underneath it, underneath the floor, underneath the ground, underneath the bedrock and the mantle and the core, the Earth is moving, the solar system is moving, the galaxy is moving at 631 kilometers per second in a direction that can be specified, toward a cause that can be partially described. And now the cause has an edge, or rather, the universe that contains the cause has an edge, not a wall, not a surface, a limit, a distance past which no information has had time to travel in the age of the universe, and beyond which the question of what exists is answerable only in principle, not in practice, not with any instrument we could build or point or wait for. That limit is the particle horizon. The particle horizon sits at roughly 46 billion light-years in every direction. The universe is 13.8 billion years old, but the horizon is not 13.8 billion light-years away. Space has been expanding during the time the light has been traveling, which means the regions that emitted the oldest light we can receive have been carried much further from us by the expansion since they emitted it. The math is not complicated once you accept that distances in an expanding universe work differently than distances in a static one. The result is a sphere, entered on the observer, with a radius of about 46 billion light-years, within which every event that has ever been in causal contact with us is contained. Outside that sphere, events that happened, but whose light hasn't reached us yet. Events that are happening now, in whatever sense now means at cosmological distances, that we cannot see and cannot know about by any means currently available. Not darkness exactly, just unreachable. The particle horizon is the edge of what we can, even in principle, know. It is not the edge of the universe. The universe almost certainly extends far beyond it, possibly infinitely. The horizon is the edge of our information, the edge of the causal past, the boundary of the knowable at this moment from this location. The horizon problem, the name given to a specific puzzle in standard cosmology, distinct from but related to what this chapter is quietly moving toward, is this. The cosmic microwave background radiation is almost perfectly uniform in temperature across the entire sky, not just in adjacent patches, across regions that, by the standard Big Bang timeline without inflation, could never have been in causal contact with each other. Opposite sides of the sky are separated by distances so large that in the time available before the CMB was emitted, no signal could have travelled between them. They had no way to communicate, no mechanism for reaching the same temperature, and yet the temperature is the same, to 1 part in 100,000 everywhere you look. This is the horizon problem. How does the universe know to be uniform if different regions of it were causally disconnected from each other before the CMB was imprinted? The standard answer is inflation, a period of extremely rapid expansion in the very early universe, before the first fraction of a second, during which a tiny region of space that was already in thermal equilibrium was expanded by an enormous factor, far faster than the speed of light, into a volume much larger than what we can currently observe. All the regions we can see today, all the way to the particle horizon and beyond, were once a single, causally connected patch. The uniformity of the CMB is a relic of that pre-inflationary equilibrium stretched across the sky by the expansion. Inflation solves the horizon problem, but in solving it, it creates something else, something relevant here. If inflation happened, and the evidence that it did is strong, the CMB power spectrum fitting the predictions of inflationary models with remarkable precision, then the universe is vastly larger than the observable volume. How much larger is uncertain. In Alan Guth's original models and most subsequent versions, the inflationary expansion was enormous, stretching the pre-inflationary patch by factors of 10 to the power of something very large, producing a universe that dwarfs the observable volume by many orders of magnitude. The observable universe, the 46 billion light-year sphere, is a small bubble within a much larger whole. The structures immediately beyond our particle horizon are real. They exist. They have mass. They have gravitational influence. And here is the thing that this chapter has been slowly walking toward. The thing that the gradual deceleration of the previous paragraphs has been building towards without announcing itself. Gravity does not respect the particle horizon. What that means requires care. It doesn't mean gravity travels faster than light. It doesn't in the relevant sense. It means that the curvature of spacetime is continuous across the horizon boundary. The distribution of mass before and during inflation shaped the large-scale curvature of spacetime in the entire universe, including the part that became our observable volume. If a large concentration of mass existed in the region that would eventually lie just beyond our particle horizon, that concentration's gravitational influence on our observable volume was established during inflation, when everything was in causal contact. The influence doesn't have to travel to us now. It was baked in from the beginning, imprinted in the curvature of the spacetime we're sitting in, a consequence of a mass distribution that we can no longer see, but whose effects persist in the geometry of the space we inhabit. Whether this actually happens, whether there are mass concentrations just beyond the horizon that are producing a gravitational influence on the local universe measurable as a bulk flow, is not established. The theoretical framework permits it. The observational evidence that would confirm it is genuinely ambiguous, but the physics does not prohibit it. The horizon is a limit on information, on causal contact in the usual sense. It is not a limit on the gravitational consequences of mass distributions that were established before the horizon existed as a boundary. There is a specific way this possibility matters for the bulk flow question. If the coherent motion of galaxy clusters extends to distances of billions of light-years, as some measurements suggest, and if the identified structures within the observable universe cannot fully account for the amplitude of that flow, then one possible explanation is a gravitational tidal field sourced partly by mass distributions outside the observable volume, mass that was in our causal past during inflation that shaped the curvature we've inherited, that continues to exert, not through any new causal contact, but through the persistent geometry of the space-time we're moving through, a gravitational influence that shows up as a coherent directional flow. This is speculative. The word matters here. Not in the dismissive sense. Speculation is how theoretical physics advances, and speculations that can be observationally tested are valuable regardless of whether they turn out to be right. But the claim that extra horizon mass is contributing to the local bulk flow requires extraordinary evidence, and that evidence does not currently exist in a form that commands consensus. What exists is the flow pointing somewhere, and the somewhere it points, when everything within the observable volume that can be identified and measured and modelled has been accounted for, still has residual, still has more velocity than the known sources produce. And the question of what accounts for the residual is where this particular subject lives at its most exposed edge. The metaphor arrives now, late, as promised. It is a simple one. Imagine a pool of water that is still on the surface, still enough that you might not notice anything's happening. But there is a very slow, very gentle current underneath, not visible from above, not disturbing the surface, but real, measurable if you put something neutrally buoyant in the water and watch it drift. You look for the source of the current and you find several pumps around the edges of the pool circulating the water. You measure the flow from each pump, you add up the contributions, and the drift of the neutrally buoyant object is still slightly more than the pumps alone produce. Either there are pumps you haven't found yet, hidden in the walls or beneath the floor, or the pool's not isolated. It connects somewhere to something outside itself, and the current has a source that lies beyond the walls of what you can directly inspect. Both explanations are consistent with the physics. Both might be true simultaneously. The pool analogy, like all analogies, can only carry so much weight. The universe is not a pool and the horizon is not a wall, but the logic of the residual, more flow than identified sources produce, pointing towards something that might be unmapped, or might be outside the mappable region entirely, holds regardless of the analogy used to express it. The particle horizon is not a conclusion. It is an edge that the question runs up against. On the near side of the edge, the surveys are doing their work, getting larger, getting more precise, finding new structures, refining old estimates, gradually narrowing the gap between identified sources and observed bulk flow. Maybe the gap closes entirely. Maybe the next generation of peculiar velocity catalogues, with hundreds of thousands of galaxies rather than tens of thousands, will find the missing mass inside the observable volume, and the flow will converge and the question will be resolved without needing to invoke anything beyond the horizon. Maybe. That is the honest word for it. The data permits this resolution. It also permits the alternative, and between the two sits the specific quality of uncertainty that this subject carries, not the comfortable uncertainty of a problem that is clearly solvable with more data, but the queasy uncertainty of a problem whose solution might require rethinking what kind of answer is possible. The horizon is not a wall. It is a place where the question changes character. On one side, the observable universe, finite but enormous, measurable in principle. On the other, whatever is there, real but unreachable, influencing or not influencing what happens on this side through mechanisms that were established before the boundary existed. In 2008, a team at NASA's Goddard Space Flight Center published a measurement that placed the source of the bulk flow explicitly outside the observable universe. They used the cosmic microwave background, the oldest light available, the relic of the universe's first transparency, as a velocity probe, measuring the subtle temperature distortions that moving galaxy clusters imprint on its surface. What they found was a coherent motion extending to nearly 1 billion light-years and pointing, they argued, toward a gravitational influence that inflation had pushed beyond the horizon. They called it dark flow. The measurement was contested immediately and has been contested since, but the question it raised has not been put away. The measurement was not supposed to show anything that dramatic. That's worth saying first. The 2008 paper by Alexander Kashlinsky and colleagues at NASA's Goddard Space Flight Center was, in its technical setup, a careful and methodologically interesting piece of work, an attempt to use a subtle effect in the cosmic microwave background to measure the bulk velocities of galaxy clusters. The technique was elegant. The result was not what anyone expected. And the result, if it holds, that qualifier has been sitting on this finding since the day it was published, points past every structure discussed in this series so far, past the Shapley Supercluster, past the particle horizon, into territory that the standard cosmological model has no comfortable place for. The finding is called dark flow. The name follows the naming convention of cosmology's other great mysteries: dark matter, dark energy, invoking the dark not as something sinister, but as something not yet illuminated, something known only by its effects rather than its nature. Whether dark flow belongs in that company, whether it is real in the sense that dark matter and dark energy are real, is genuinely unsettled. This chapter is going to sit with that unsettledness rather than resolve it, because resolving it would require pretending the evidence is cleaner than it is. The technique Koszaliński's team used is called the kinematic Sunyaev-Zeldovich effect. It is worth understanding because the technique is clever in a way that makes the result feel more trustworthy than a simple position measurement, and understanding why it was trusted initially helps explain why the subsequent challenges landed the way they did. Galaxy clusters are enormous concentrations of matter, hundreds to thousands of galaxies plus vast quantities of hot gas, bound together by gravity into structures that can span tens of millions of light years. The hot gas in a cluster, heated to temperatures of tens of millions of Kelvin by the gravitational compression of the cluster's formation, emits X-rays and also scatters photons from the cosmic microwave background. When a CMB photon passes through the hot gas of a cluster, it can gain or lose energy through inverse Compton scattering. The electron kicks the photon to a higher energy. This is the thermal Sunyaev-Zeldovich effect, observed in clusters since the 1980s and now a standard tool in cosmology. The kinematic version is different and subtler. If the cluster is moving relative to the CMB rest frame, if it has a peculiar velocity, then the scattering introduces an additional temperature shift in the CMB in the direction of the cluster, a shift that depends on the component of the cluster's velocity along the line of sight. The effect is tiny, about 10 times smaller than the thermal effect. It had never been directly detected in an individual cluster before Koszaliński's work, but Koszaliński's team realized that if you look at hundreds or thousands of clusters simultaneously, the individual noise averages down and the coherent signal, if there is one, becomes detectable. They assembled a catalogue of about 700 X-ray selected galaxy clusters, reaching out to distances of roughly 6 billion light-years. They cross-matched this catalogue against the WMAP satellite's 3-year map of the CMB, and in the combined signal they found a coherent motion. All the clusters, at all distances within their sample, moving in roughly the same direction, at speeds of 600 to 1,000 kilometers per second, toward a patch of sky between the constellation Centaurus and Vela. 600 to 1,000 kilometers per second, coherent, not diminishing with distance. That last part is the important and troubling part. In the standard picture, bulk flows should decrease with increasing distance. The influence of any local mass concentration, Shapley, the Great Attractor, the Dipole Repeller, falls off with distance. A galaxy cluster 100 megaparsecs away is more strongly influenced by local structures than a cluster 500 megaparsecs away, which is more strongly influenced than one at 1000 megaparsecs. The bulk flow should converge as you go further out. That convergence is what all the peculiar velocity surveys were trying to demonstrate or characterize. Koszaliński's measurement showed no convergence. The clusters at 300 megaparsecs were moving in the same direction at roughly the same speed as the clusters at 600 megaparsecs. The signal didn't change character with distance the way a locally sourced flow should. It behaved instead like something very far away, something so far away that the distance gradient across the entire survey volume was negligible, because the source was much, much further than the survey extended. The matter in the observable universe, Koszaliński said, simply cannot produce the flow we measure, The source must lie beyond the horizon. The proposal, careful in the paper itself, more vivid in the press releases and interviews that followed, invoked inflation. If inflation expanded the pre-inflationary universe by the enormous factor that the CMB evidence suggests, then the universe beyond our particle horizon is real and populated, and, presumably, lumpy. Mass concentrations exist out there, very large ones possibly, given that the scale of structure formation outside our volume had no reason to produce only what our local patch produced. If one or more such concentrations happen to form in the right direction at the right distance, pushed there by inflation's expansion, no longer visible to us, no longer causally connected in any conventional sense, then the curvature they imprinted on space-time during the inflationary epoch could persist as a tidal gravitational field within our observable volume, manifesting as a coherent directional flow that doesn't diminish because its source is effectively at infinity relative to any structure we can map. That is an extraordinary claim. It requires structures beyond the observable universe to be gravitationally influencing our local cosmic flows, through a mechanism established before the particle horizon became a boundary. It is theoretically coherent. The physics doesn't prohibit it. It is observationally extraordinary. It requires evidence of a quality and consistency that the 2008 data alone couldn't provide. The community received it accordingly. The criticism came quickly. Edward Wright at UCLA posted a detailed analysis within weeks of the paper's appearance, arguing that Kashlinsky's team had not properly accounted for primary CMB anisotropies, the intrinsic temperature fluctuations in the microwave background that are large, compared to the kinematic SZ signal and can, if not handled carefully, create spurious coherent patterns in exactly the kind of cross-correlation analysis Kashlinsky's team performed. Wright's critique was technical, specific, and serious. The Kashlinsky team responded, defending their methodology, arguing that the primary CMB contamination was accounted for in their analysis. The exchange was substantive and the disagreement was genuine. Kashlinsky's team extended their analysis. In 2010, they published an updated measurement using 5-year DUMAP data and a larger cluster sample, about 1,400 clusters. The flow persisted. In a second 2010 paper, they pushed to distances of roughly 2.5 billion light-years, doubling the depth of the original measurement. The flow persisted there too. The signal in their analyses seemed robust. They extended its reach with each new dataset. And then Planck launched. The Planck satellite, the European Space Agency's successor to WMAP, produced the most detailed and precise map of the CMB ever made. Higher resolution, lower noise, better control of systematic effects. When Planck data became available in 2013, several teams performed independent searches for the kinematic SZ bulk flow signal using the Planck maps and large cluster catalogues. They didn't find it, or rather, they found a signal consistent with 0 at the scales Kashlinsky had claimed, with upper limits that ruled out a bulk flow of the amplitude his team had reported. The 2013 Planck analysis of the kinematic SZ effect found no evidence of dark flow. This was a significant challenge. Planck's data quality was substantially better than WMAP's, and an independent non-detection at Planck sensitivity was hard to dismiss. But then, in 2015, Fernando Atrio-Barandela, a longtime collaborator of Kashlinsky's, published a reanalysis claiming to find support for the dark flow in the Planck data, arguing that the 2013 Planck analysis had used an insufficiently complete cluster catalogue and a methodology that was less sensitive to the signal than Kashlinski's original approach. The 2015 paper claimed the flow was still there. The Planck team and other independent groups maintained their non-detection. The situation as it stands, and it is standing still, unresolved, the definitive paper that settles this question has not been published, is genuinely ambiguous. The original measurement was real in the sense that the data showed what it showed. Whether the signal in that data is a physical bulk flow or a methodological artifact is contested. Whether Planck's non-detection is definitive or methodologically insufficient to detect the claimed signal is contested. The field has not converged. I find this particular controversy more interesting than most, and I want to be direct about why. Because the reason is not the drama of a disputed result, which is common enough in cosmology. What makes it interesting is the specificity of the claim. Kashlinski didn't say the flow was anomalously large. He said the matter in the observable universe cannot account for it. That is a precise, falsifiable, extraordinary statement, and it is the kind of statement that science needs in order to make progress. If dark flow is real at the amplitude reported, it is not a minor revision to the standard cosmological model. It is a detection of gravitational influence from beyond the observable horizon, the first and by definition the most distant gravitational signal ever measured. The implications for inflation models, for the structure of the pre-inflationary universe, for the question of what lies beyond our cosmic horizon are not small. If it is a methodological artifact, if the signal is an imprint of primary CMB anisotropies on a cross-correlation that didn't account for them cleanly, then it is a cautionary story about the difficulty of extracting very small signals from very noisy data and nothing more. The evidence right now does not clearly distinguish between these possibilities. The honest position is that there is a specific quality to sitting with a result that might be the most important measurement ever made in cosmology, or might be a systematic error. It has a texture I can only describe as weightless, or not weightless, the opposite. Too much weight distributed over too much uncertainty, pressing evenly on every surface with nowhere for the pressure to go. I was reading through the original 2008 paper late one night, the actual paper, not a summary, sitting with the tables of cluster data and the signal maps and the careful hedged language of researchers who clearly knew what they were claiming, clearly knew how it would land, and I found myself going back to one sentence in the abstract repeatedly. The matter in the observable universe just cannot produce the flow we measure. That sentence. Set down in the quiet declarative tone of a technical result, as if it were just a number that didn't add up, as if it were ordinary to say, the visible universe is insufficient to explain what we see. Whether it's right or not, the sentence identifies the exact location where this entire subject, the peculiar velocity of the local group, the Great Attractor, Shapley, the bulk flows, the zone of avoidance, all of it, converges. Everything in the preceding chapters has been building toward the question that sentence poses. The observable universe might not be the whole story of what is pulling. The pull might reach from somewhere we cannot see, and whether or not dark flow is the evidence for that, the question itself is real, and the possibility it opens is not going away. The direction of the dark flow in Kashlinski's measurements is roughly consistent with the direction of the local group's peculiar velocity. Both point toward a region of sky in the direction of Centaurus and Vela, roughly aligned with the CMB dipole. Whether this consistency is meaningful, whether dark flow and the local group's bulk motion are two manifestations of the same underlying gravitational source, or whether the directional similarity is coincidental, is part of what makes the interpretation difficult to discard even as the detection itself remains contested. The coherence is either a clue or a coincidence. In cosmology, distinguishing between those requires more data than currently exists. What the dark flow controversy does, regardless of whether it is ultimately confirmed or refuted, is make explicit what the previous chapters had been approaching implicitly. The question of what is pulling the local universe is not closed. The identified structures, the Great Attractor, Shapley, the Dipole Repeller, account for most of the observed peculiar velocity. Most. The residuals are smaller than they used to be, but they persist, and the persistence of residuals in a subject where each new survey has found something new in the direction of the flow carries a particular kind of weight. Something is there, whether it is simply unmapped, or whether it requires a source that transcends the observable boundary. That question sits open tonight in the data, waiting for a measurement precise enough to answer it. What is certain, while the answer waits, is the motion itself, the fall, the direction, the 631 kilometers per second that the body in the room has been accumulating quietly, in a direction the data can name but the surveys cannot yet fully explain. The room is still here. Whatever room it is, the specific ceiling, the specific weight of the air, the sound the building makes when the temperature outside drops and the walls contract slightly, and the whole structure shifts. It is still here, present and immediate, and close, in the way that only physical things nearby can be close. The body is in it. The blanket has whatever weight it has. The dark is the particular dark of wherever you are tonight. Not a general dark, not a conceptual one, but the specific quality of light absence in this room at this hour. And the room is moving at 631 kilometers per second. That fact hasn't changed. It was true at the beginning of this, and it is true now, and the hours between haven't altered it, haven't explained it away, haven't resolved the question of what exactly is responsible for the last few % of that velocity that the identified structures cannot account for. The motion was accumulating before any of this was narrated. It will be accumulating after. The narration doesn't touch it. What changes, maybe, is the texture of the fact, not the fact itself. The fact is fixed, measured, repeatable, sitting in the CMB dipole like a number engraved in the oldest light in the universe. But the texture of knowing it, whether it sits in the mind as a piece of trivia or as something with genuine weight, depends on how long you stay with it, how many layers of context you let accumulate around it. The Great Attractor was a name before it was a location. Shapley was a cloud in a photographic survey before it was a cause. The Dipole Repeller was an assumption nobody had thought to question before it was a discovery. Each of these things required decades of work to become what they are, and the work is still going on, and the number 631 is still slightly too large for everything that's been found to explain. There is something specific I want to say about what it means to live inside a motion you cannot feel, not philosophically, not as a prompt for reflection about the human condition or the smallness of our perspective, or any of the things that popular science writing often gestures toward when it reaches this kind of fact. Just, practically, physically, what it means to be matter that is moving directionally through the universe at a speed that would cross the continental United States in roughly 5 seconds toward a cause that is only partially identified, in a motion that has been ongoing for longer than the planet has existed. It means nothing changes about the room, the walls don't vibrate. The water in a glass on the nightstand doesn't slosh toward one side, the blanket doesn't shift. The motion leaves no trace on anything at the scale of the body, the room, the building, the city. It is, in the most literal possible sense, imperceptible. You are moving at 631 kilometers per second right now, tonight, and there's absolutely nothing about that experience. No sensation, no evidence, no physical consequence at human scale that differs from being at rest. The only way to know is to look at the CMB, to compare your velocity against the oldest light in the universe and notice the Doppler shift. And when you do, when the instruments make that comparison and the math extracts the number, there it is, real, measured, pointing somewhere specific. The something it is pointing toward, the ensemble of causes that together produce the 631, has been the subject of this long night. The Great Attractor, real and partially resolved, the Norma cluster sitting at its core, behind a curtain of galactic dust. Laniakea, the basin defined not by what is there, but by which way things fall, 500 million light-years wide, the Milky Way somewhere near its outer rim. Shapley, found in 1930 as a cloud in a photographic survey and understood as a gravitational force decades later, the most massive concentration in the local universe, contributing somewhere between 1/4.5 of the peculiar velocity depending on how the accounting is done. The Dipole Repeller, the void pushing from the other side with a force roughly comparable to the pull from Shapley. The push that the attractor-only picture had been missing for 30 years. And then the residual. The small, stubborn, consistent excess in the bulk flow that the identified sources don't fully explain. The flow that keeps pointing, past the surveys, past Shapley, towards something either unmapped inside the observable volume or, this, outside it. The dark flow measurement contested, ambiguous, possibly a systematic artifact and possibly the first detection of gravitational influence from beyond the particle horizon. Still open, still unresolved, still sitting in the data, waiting. I want to stay with the residual for a moment, because I think it's the most honest place to end. Not the dark flow controversy specifically, that's a technical dispute that will eventually be resolved by better measurements one way or the other. The broader residual. The fact that in a subject this well studied, with this much data, with surveys spanning decades and teams on multiple continents and instruments of extraordinary precision, there is still a small but persistent gap between what is known and what is observed. Still, a part of the Milky Way's motion that points past everything that has been named and measured and mapped. Science is often presented as a process of closing gaps. Find the question, build the instrument, gather the data, close the gap. And it is that. But it is also a process of discovering that the gap is a different shape than you thought, or that closing one part of it opens a new part, or that the gap, looked at from close enough, is actually the edge of something larger than the question you were originally asking. The peculiar velocity of the local group started as an anomaly in early galaxy surveys, became a question about local mass distributions, it became the Great Attractor, became Laniakea, it became the Dipole Repeller, and now it sits, still partially unexplained, at the edge of what current instruments can reach, pointing, some analyses suggest, at gravitational influences that may lie beyond the boundary of the observable universe itself. That trajectory is not a failure. It is what genuine scientific questions do when they're asked honestly and pursued seriously. They get larger. The atoms in the body have been in this motion for the entire history of the solar system. Before the Earth formed, the molecular cloud that would eventually become the solar system was already falling. Slowly, cosmologically slowly, but falling. In this direction. Before the sun ignited, before the first rocky planetesimals clumped together in the protoplanetary disk. The material that would eventually become you was already participating in this flow. It was part of the local group before the local group had a name. It was inside a Laniakea before Laniakea was defined. It was being pulled by Shapley for billions of years before Shapley was photographed, named, characterized, and understood as a cause. The motion is not new. What is new is knowing it is there, and knowing changes something even if it changes nothing about the physical situation. The room is still moving. The velocity is still 631 kilometers per second. The destination, if destination is even the right word for a point that the expansion of the universe is likely carrying away faster than the full can close the gap, is still Shapley or something behind Shapley, or something that the surveys haven't reached yet. None of that is affected by whether anyone knows it or names it or spends a quiet night thinking about it. But there is a specific quality to lying still and knowing, actually holding the knowledge rather than just having encountered it, that the matter of the body is in directional motion toward a cause. That is only partially understood. That has been identified piece by piece over decades of work by people pointing instruments at an obstructed sky and arguing over the interpretation of residuals in noisy data. That specific quality isn't wonder exactly. It isn't awe in the way that word usually gets used. It is more like a shift in the weight of the ordinary. The room is still just a room. The ceiling is still the ceiling. But the ceiling is moving, and the direction it's moving in has a name, and behind the name is a genuine open question that the best current science cannot fully close. That seems worth knowing even at this hour, maybe especially at this hour. Before this night settles completely, this channel exists because of people who believe that physics belongs in the quiet hours. No studio, no production company, no algorithm chasing, just research, writing, and time spent trying to make the universe feel as strange and as close as it actually is. If that's something you want to support, the Patreon link is in the description below. Even the smallest contribution keeps this work going, and for those already there, the fact that you're there is what makes projects like this one possible. It matters more than the numbers suggest. Everything here is self-funded and made by one person, and it stays that way by choice, because the work is better when it doesn't have to answer to anything other than the subject. If you found your way to this channel and this video has been worth your time, consider visiting the Patreons. There's no pressure, no sales pitch, just an open door for the people who want to keep this space alive. The fall continues tonight. While this is being heard, while the room is dark and the body is somewhere between awake and not, the Milky Way is covering 631 kilometers for every second that passes. The local group is moving. The matter in the blanket, in the pillow, in the slow rise and fall of breathing, all of it, heading in a direction the CMB records and the surveys partially explain and the best current instruments point toward without fully resolving. The Great Attractor is real. Shapley is real. The Dipole Repeller is real. The residual is real. What lies at the end of the residual, what the flow is ultimately pointing toward, whether it is a structure inside the observable volume that hasn't been mapped yet, or a gravitational tidal field established by mass that inflation pushed beyond the horizon, is genuinely unknown. Not unknown in the comfortable sense of a solved problem awaiting confirmation. Unknown in the full sense of the word, unsettled, open. Being worked on right now, tonight, by people running peculiar velocity catalogues and arguing about systematic errors in kinematic SZ analyses and planning the next generation of surveys that will either find the missing mass or confirm the gap. And the gap, if it confirms, will be the first evidence that something outside our universe is reaching in, or it won't. The next survey might close it entirely. Both of those outcomes are worth staying awake for. Neither requires anything of you right now. At this hour in this room, the falling will continue either way. It has been continuing for 4 billion years, and it will continue after every question raised tonight is answered, and replaced by the questions those answers open. The room is still. The motion is real. The direction is known. What's at the end of it? That stays open. For now, the only thing required is this: the dark, the weight of the blanket, the particular ceiling of wherever you are, and the quiet knowledge that the matter of you has been falling towards something vast and only partially understood for longer than the word falling has existed. Let that be enough for tonight. Rest now. The universe will still be moving when you wake up, and there will be more to say about it on another night, in another quiet hour not unlike this one,